Is it good? Can you hear me? Okay. Online is okay. Okay. Let me just reduce this volume. Better? Okay. Know what's wrong with these things? They always come to my eye. Did we scare a lot of people yesterday? Hopefully that's a good thing. If you're scared so early, then maybe it's good to be scared. Or maybe it's a usual Friday in Switzerland where no one does anything except for hardworking people. Good to be critical. Okay, let me log into Zoom. Do we publicize the Zoom link for students here? Zoom link, do we publicize it to the students? Can they join via Zoom? Okay, it's on the course page, okay. That's a place where people can join and ask questions if they want. I mean, they can ask questions on YouTube also, but that has to be text-based. Okay, let's get started. It's time, right? 1:16, yes. Okay, today we're going to continue what we started yesterday. Let me change this a bit. And we're going to cover more on memory systems. But I want to give an overview, very quick overview of what we did yesterday briefly. And then we're going to get into memory systems. But I also want to cover course logistics in the middle somewhere. Let's see where that will be. Oh, okay. Maybe people are trying to find the room. Is that the okay? Yeah, that's what happens, I guess, if you have two different rooms. Why do we have two different rooms? Okay. Okay. We like that room and this room. And then they don't like, they cannot give both of them at the same time, or anyway, it doesn't matter. Now that you figured it out, you can come more easily next time. That's that's prediction. And you can optimize the path, reduce the latency, you can do all of those optimizations. That's business as usual once you know something. Okay, so let's get started. Why isn't this working? Maybe it's just, okay. So yesterday we talked about some things. I'm not going to cover them again. I think a lot of that was mindset setting. And we talked about why study computer architecture. We talked about enabling better computing platforms. We saw some examples of computing platforms that people are designing today, which was hopefully interesting. We're going to see some more during this course. And we discussed why we do computing. We took a critical approach to it. And we also discussed what kind of metrics we want to optimize for going into the future. Let's just to remind you, jog your memory. We talked about robustness. We're going to talk more about that today, and especially later in a few lectures. We talked about sustainability, energy efficiency. We're going to talk a lot more about that again. We may talk about it today, actually, with some metrics. We're going to talk a lot about high performance, and we talked about the importance of still pushing for high performance to solve real problems. But of course, as you push for high performance, you also create problems. That's the unfortunate thing, right? There's no solution. And this is, again, technology is agnostic to ethics or morality, right? People will use high performance for bad things. People will use high performance for good things. And you cannot prevent people from doing bad things in the world, I think. Maybe most of the world is doing bad things, right? So we're in the minority, I guess. Yeah, it's a tough world. But nobody said the world would not be tough or fair. Anyway, but that's important. I mean, pushing for high performance comes is a double-edged sword in the end. Right? Okay, personalization and privacy is important also, and this will become more important. We've discussed that also briefly, but we will do more of that in the course of these lectures. We'll have, for example, some cutting-edge research on how to do processing on encrypted data using homomorphic encryption type of techniques. and how to accelerate it, because currently the algorithms to do that is really slow. And I think it's going to be important to make that extremely efficient so that you can actually keep the privacy of the data without any leakage and do the processing without encrypting the data and not reveal anything to anyone. Again, this could be used for good things and bad things, right? And if you're thinking about, for example, blockchain, etc., it could actually have very good applications in those areas, but also in many other areas like genomic analysis. Does that sound good? Okay, so this course, as you can see, covers a lot of interesting things, hopefully. Yeah. Okay, we also discussed how do problems get solved by electrons. And I put up my favorite slide, which is humans communicating with electrons. And we discussed why that's not possible today. But it's good to strive for making it possible, maybe. Maybe these smart AI people should be working on this sort of issues as opposed to tweaking LLM X, LLM Y, LLM Z, so that they can make billions of money or whatever, right? I think we have a problem with smart people working on tweaking stuff as opposed to doing something really interesting. How do I communicate with the electron with my technology, right? Hopefully, I don't know. I'm not going to provide them money for it, but they should be intrinsically motivated for doing things like this as opposed to tweaking LLMs, which is another critical view that I have, as you can see, right? I see a lot of tweaking LLMs going on. Probably papers, like 100 papers, 500 papers, 1,000 papers that are written every year. In my opinion, they're all going to be forgotten. It's kind of a waste, right? If you think about it. We're going to take a critical view of computing systems. There's a huge waste in computing systems, but there's an even bigger waste in research today, right? These people are doing things that are not going to be interesting, in my opinion. Then you could argue that, of course, these small things will lead to something big. Yes, there's also a possibility like that, but not all of the world's resources should go to that thing, right? There's a lot of other stuff, right? There's a big hype in AI. There's a big hype in quantum computing. And I think these are interesting things to examine, but not all of the world's resources should go to AI or quantum computing. In fact, quantum computing, I think, is very, very limited in the applications that it can enable currently. But there's a potential. But we already have a lot of things that we can do in existing systems, like what we're going to talk about in these lectures. So I think it's good for people to have a good perspective of these things, right? Don't be just, let's say, swayed by the hypes of the day, because there are always hypes of the day that are going to come and go. The question is what is fundamental and what we should be really doing research on. And from my perspective, research should be distributed across many domains, and we should really have progress across many domains. Okay, so it's good to think about it. Okay, so I digress, but I like digressions, I guess. So we discussed that this is the narrow view of computer architecture, which you may have seen in your computer architecture course. And we've discussed in DDCA and FOCA, for example, but we always take a broader view in this course because of reasons we discussed yesterday also, because it's very hard to make big changes to the system if you're constraining yourself to a very small fraction of the system. If your constraints are too much, basically, you cannot innovate easily. But if you actually reduce the constraints, you can innovate more easily. Again, I will have some other slide later about that maybe at some point. But if you want to improve energy efficiency, let's say by 100x, it won't come from a very simple tweak at one of the layers. Maybe if you do materials and extremely efficient materials, but to enable those materials, you need to build circuits and devices using those materials, right? The material may be very promising. It may actually have a promise of 100x energy efficiency, but if you don't build the things on top of it, you may actually not get that huge energy efficiency. As we will also see, without going into materials in this course, we're not going to change the materials that which we're going to build with computing with. We're going to use even actually very old materials like charge-based capacitors. And we're going to see you can actually get a lot of performance improvements, energy improvements if you change the paradigm and change the software and hardware stack on top of it. Hopefully that makes sense. Hopefully that gives you an idea. Okay. Oh, I'm not working with this one. So, okay, these are some slides that we discussed yesterday. I'm not going to cover them again, but there are a lot of opportunities in studying computer architecture. These are some, like, let's say, still within the domain opportunities. You can enable better solutions, new applications, better systems. And we discussed that today is a very exciting time to study these concepts because a lot of things are possible today. Like a lot of the pictures that I showed you yesterday of computing systems, I couldn't have shown you those pictures 10 years ago. And certainly when I was studying computer architecture, those pictures weren't there. It was just Intel processors, AMD processors. AMD was actually not doing very well. Today they're doing very well because they handled some things better. But Intel's almost dead, as you remember from yesterday. Okay, hopefully it won't be dead, but it's going to be difficult. It needs a Lazarus, I guess. Okay, yeah, we've discussed this also. I'm going to skip this. Basically, today, every component and its interfaces, as well as the entire system designs, are being re-examined. And we're going to look at essentially everything in this picture, I would say. We're going to look at, start especially with memory. And we're going to talk a lot about memory and then storage. And we're going to talk about how to exploit parallelism, handle bottlenecks, multiprocessor design, accelerator design, etc. Okay, but we're going to always take this expanded view because we want to achieve highest efficiency, performance, robustness, etc. At some point, I'm going to switch to course logistics, but maybe I'll ask you when. Any questions? Yesterday, there were some questions. Any more today? Okay, you're still getting ramped up. So this course will actually look at, even this lecture, we're going to look at things at the lower level of the stack, as well as the higher level of the stack. But I think it's important to also think about what can you do at each level. And again, there is a sentiment sometimes that the lower level is not important. And this usually comes from these high-level software people who know nothing about hardware and devices. Again, this is a critical view, as you can see, right? There's some fluff that's going on at the software level. People have no idea about how a computer works, even though they have computer science degrees. I think this is dangerous. We should not be giving computer science degrees for people who don't know how a computer works. I have a very strong opinion on this one. Unfortunately, we may be. The good thing is, at ETH, at least we have the course developed by Niklas Wirth, where we teach how a computer works to computer science students. That's not the case in many places in the world. But basically, there's a sentiment in this high-level fluffy folks who are working on all of these high-level concepts that some magic happens and computer executes programs, right? And we don't need any more of that, right? But this magic didn't happen in a magical way, right? People actually developed a lot of things to make these computers work at the hardware level. So it's really important to understand that. And when you go into whatever job you go into, counter those fluffy people, I would say, because they're really diminishing what people have done over 80 years or so to make this hardware really work. This thing in my pocket is better than a supercomputer 20 years ago, maybe even 10 years ago. I haven't done the calculations. But essentially, it's because of the hardware. It's not because of the fluffy LLM that someone actually built, right? And that fluffy LLM executes on this hardware because of that hardware, right? So it's good to think about that. So I think there's still a lot of room at the bottom for those who have their eyes open, as opposed to for those who may actually have their eyes closed, right? So this is Richard Feynman, who is an amazing teacher. If you have listened to his lectures, I would recommend doing that. He's a physicist. He was a physicist. He's not alive anymore. But essentially, this is an article, not an article actually. It's a talk he delivered, lecture he delivered, as you can see over there at Caltech, where he worked. And he basically said there is plenty of room at the bottom. This is 1959. And I'm saying the same thing in I cannot move. I'm saying the same thing in 2025, basically. I'm stealing this phrase from him, but I'm quoting him, so it's not called stealing, right? As you can see. Basically, there's still plenty of room in the bottom. So what did he say at the time? Basically, he was a visionary. He basically thought we would like to directly manipulate individual atoms so that we can do better synthetic chemistry, better nanoelectronics, whatever, essentially. So this is a vision, as you can see. Today, we cannot do it, clearly. We cannot directly manipulate individual atoms, but we're getting close, essentially. And you can read about it if you want. And I think this sort of thinking essentially was inspired by the need for denser computer circuitry, because we're really dealing with atoms at this level. Microscopes, like scanning electron microscopes used for different things. He had a lot of other visions, like swallowing the doctor, for example. If you actually can do this nanoscale machines, you can build small robots who can actually go in your body and do different things and attach themselves to different things over there, right? So this is the vision, basically. And if you don't have that sort of vision, then you're not going to build anything. That's really interesting, in my opinion, right? This sort of vision, the belief that there's plenty of room at the bottom, enabled the advances we have in computer circuit. And clearly, he's not the only one, right? There are many people, including the visionary founders of Intel, for example, not the current people who are trying to, let's say, save that company, but the visionary founders. They actually enabled a lot of progress. And that hardware actually enabled a lot of things. So that's the low level, basically. So there's a lot of things that can be done at the bottom. And I think there's a lot more we need to find out, because we're having a lot of trouble, as you will see today, with existing technologies. Even though we should do more to actually make existing technologies work better, I think we really need to look more into newer technologies, not just quantum computing. I'm not just talking about quantum computing. I'm talking about things like carbon nanotubes, different type of materials, where we can build computers with the same principles, well, or better principles than what we have today. It doesn't have to go to quantum computing, which I don't know what fraction of people understand in the world. So it's good to think about that also. Right? It needs to be a little bit more intuitive for people to work with. Right? Okay, so that was a critical view, but there's also, so some people at the top think that this doesn't exist. So it's good to deconstruct what they think. A lot of people believe this part, which is there's plenty of room at the top, and this makes sense. And these people basically wrote a paper pointing out the obvious, which a lot of people knew, but they just wanted to write a paper, I guess, which is a good paper, actually, not bad. But essentially, this paper says that because scaling of the technology at the lower level is not going well, we can do a lot more at the top, rethinking the software, rethinking the algorithms, rethinking the architectures. Obviously, that's true, yes. Because if you're not scaling at the hardware level, you should be much more efficient at the software level, right? At the higher levels. And that's what this paper is. It's a good paper, actually. It's good to read it. But in a sense, it's nothing new in that sense. Right? It's good to think about that. Okay, so you can see over there, basically opportunities for growth in computing performance will still be available, even though hardware scaling may not go well. Then we need to focus on other things, making software algorithms and hardware architecture a lot more efficient. And that's true. But I would argue that this part is not completely true. Semiconductor miniaturization is running out of steam as a viable way to grow computer performance. There isn't much more room at the bottom. This is wrong, in my opinion. This is thinking existing technology, right? Basically, if you think about new technologies, the goal is to enable those. You cannot just give up. There's no more room at the bottom. Let's not do anything. Then you guarantee there's no more room at the bottom, right? This is like self-fulfilling prophecy. It's a very bad self-fulfilling prophecy, in my opinion. Does that make sense? So I think people should not make statements like this. Let me put it that way. This is a dangerous statement. This is an okay statement, right? Okay, anyway. By the way, I have a lot of respect for these people, but still, we got to be careful in what we channel future generations into. Okay, so in my opinion, there's plenty of room both at the top and the bottom, because we have a very unoptimized system today, the way it's designed. And we need to actually research both levels, at the bottom as well as the top. But we also have another problem, right? Which is really the communication optimization that we do across the stack. So the bottom and the top is very disjoint from each other today, right? There are people who write software who have no understanding of what's going on in hardware. And let's take a critical view against the hardware people also. There are people who design hardware who have no idea what the software is about, right? In the end, these people are trying to design a computing system without much communication, right? And if you don't have that sort of communication that enables optimizing across the stack, across the system, then you'll have a suboptimal system by definition. Right? Basically, that's the approach that we take. That's why we want to have this expanded view. But this expanded view of computer architecture should be enabled with proper communication mechanisms across the stack, from the hardware to software. For example, what kind of abstractions should hardware provide such that the software can execute different types of code very efficiently, right? Are our current abstractions good? Should we go through a general purpose ISA, instruction set architecture, where the software is compiled into a sequence of instructions that are executed sequentially? And can we actually do this much better, or can we do this in a much better way? Maybe we can customize that for programs. Maybe we can make that more flexible, such that software programmers can express different types of operations as opposed to limiting themselves to a set of instructions, right? So it's good to think about this. And I think today we're kind of limited with this ISA. But the good news is, again, because of the difficulties in improving energy and performance, people have been designing these accelerators. And those accelerators have very different interfaces to the software, because now you can actually, you don't necessarily have to, for example, you don't necessarily have to have instructions. You can actually use an FPGA and program the FPGA such that it can execute an important part of the program, right? So that's another interface. And that may be a better communication. But again, there are issues over there that may not be as easy, because if you have an FPGA programmable hardware fabric, there's a lot of waste in that to make it fully programmable. And now you need to overcome the inefficiency of the hardware with some software techniques. Right? If you have an accelerator like a systolic array, like we discussed yesterday, which is really the only thing that it does really well is, let's say, matrix multiplication, then you can optimize the software for it. But again, once you optimize the software for it, the improvements at some point will not be good enough, right? So you'll need to invent some new hardware to actually get to higher efficiency levels. So it's good to think about this, because every time you design some hardware, you'll need to optimize the software. And at some point, you run out of steam, right? The question is, what do you do at that point, right? You design some new hardware? That's a good idea, yes. That's how things have evolved over time, right? Especially with machine learning, for example, recently. But you still need to communicate well, because once you design new hardware, the software may not be optimized for it. Okay, I spent a lot of time on the slide because it's actually the core of what I think. There's no, in my opinion, there's no debate. There's people who say there's no more room at the hardware or low level bottom, let's say. I don't think they're right. People who say there is no more room at the software, or we should not optimize software, they're not right. There are very few people who say that, in my opinion. I think everybody understands that software is terribly optimized in general, and we should really optimize it and make it efficient. But people may not understand hardware as much. It's good to think about the law of large numbers, right? If you think about it, most of the people who deal with computer science are software designers. They're very high-level people. They use Python and they think Python is a computer. How many people here think Python is a computer? You think Python is a computer? Okay, tell me why. Well, okay, sure, but is that a computer? Turing complete. Oh, then any language is like that, right? Okay, there you go. I think that's the. Okay, maybe I'll ask the question in a different way. Python is something that executes on its own and there's nothing underneath it. Yes, exactly. Yeah. But those abstractions can be good for some things like productivity. But those abstractions are terrible if people start making statements like, oh, we don't need anything else, right? So it's good to think about that, right? Yeah. Abstractions are good for productivity in general. But if that's the only abstraction you know, you're very limited in what you can do. Meaning, you know this abstraction, you know nothing underneath. You have no idea how this thing executes. You cannot optimize things. What if it breaks? What if it's slow? What if it's inefficient, right? Then you go to someone smarter or someone who actually invested more in learning as opposed to someone who just wanted to be a Python programmer, right? And probably you could be replaced by AI easily. That's also good to think about. And I do hope actually that happens, frankly, not because I think jobs should be gone, but I think we can be much more efficient if we can replace a lot of these, let's say, not so interesting repetitive jobs with AI. And maybe if we do the right thing over there, it can enable us to be much more efficient in discoveries, etc. Right? We're not there yet, but I think it's good to push forward. And I think humans, you should use this thing over here that that developed over, let's say, many millions of years. It took a long time for this to become like this. For, let's say, really important and interesting things, right? Anyway, okay. That we digressed, but it's good that you challenged me. I like that. Not everything Turing complete is a computer. Now we need to go to the definition of a computer. Okay. Okay, so that's why we have this expanded view. Okay. Okay, let me discuss this, and then I'm going to jump to course logistics at some point. I don't know when, but basically this course will ask a lot of this question. What limits us in computing today? I mean, clearly our mindset limits us. So that's really important to recognize at the very beginning, right? The mindset of people, that they don't believe something better could be done, for example. I'll give you another example, right? You've taken DDCA, and I gave this example in DDCA. Some of the people over there have taken DDCA, and we cover the MIPS architecture. MIPS is one of the ISAs, instruction set architectures. And when people designed the MIPS R2000 in 1980s, some people claimed this is the best computer we can design. This is a 5-stage pipeline, in order, boring machine. If you've taken DDCA, you can do this easily. Some people claim this is the best computer we should design. We should not invest into hardware. It's beautiful, clean. We don't need more performance. I don't need to say anything else after this. Now you can imagine how stupid this sounds today, right? If you take a 5-stage pipeline in order, it's not going to do much on any interesting workload, let alone the AI stuff that people are optimizing for today, right? So it's good to think about that, basically. Whenever people said, we've designed the best thing that performs good enough, that's the end of innovation, basically. Let them help. Let them help themselves do innovation with that hardware, but don't disregard them and develop your own hardware. And those people who are the innovators will actually do the best things. Okay, anyway, this course is in part about questioning, essentially. Questioning what limits us in designing the best computing architectures for the future. And we're going to question a lot. And maybe if I don't question enough, you question. That's how the world becomes better, right? I can question only so much by myself, but collectively, if people question concurrently, there will be a better future. That's why I like you challenging me. And I would encourage that, right? And hopefully providing directions for fundamentally better designs. And again, I will provide some directions based on what I know, but it's even better if there's more brainstorming that happens and people think differently, because we do need that different thinking today much more than any other time in human history, in my opinion, in computing design, clearly, because we're having a lot of issues, as we will discuss and as we have kind of discussed yesterday. And hopefully, I will try to advocate principled approaches as much as possible, because I think we need to be very principled in how we develop things, especially design things. And I think we're violating some fundamental principles when we design computing systems today. And we're going to get to that soon. Does this sound good? Maybe a little bit different from the courses that you're used to, which basically teach how things work. And you're not supposed to question them in general. I don't like those courses in general, but there's a value in undergraduate courses doing that clearly. But this is a graduate course. Remember, undergraduate courses are supposed to build your background. And again, it's always good to add an element of questioning over there, as I do in DDCA, for example. Even though I teach, for example, sequential execution, von Neumann architectures in digital design and computer architecture, I also say this is not the only way to design computers, even though it's the dominant way today. There are other ways. For example, we talk about data flow architectures, right? And again, data flow is actually a nice paradigm today that's useful for machine learning. When I was talking about this in 2009 or so, again, it was not as useful, even though it's really at the underlying hardware of all out-of-order execution engines, as you know, if you've taken DDCA. Okay, let's see. So what limits us today? So I'll tell you what doesn't limit us. Well, maybe or limits us in the sense that we cannot really handle these things. It does limit us, basically. Applications will come. People are very good imaginers, even though it may be a small fraction of them. They invent new applications, they dream, and applications will definitely come. So we're not going to be limited by people's imagination, in my opinion, unless we replace people with AI, and then we will be limited terribly. Hopefully that won't happen, at least not in the creative domains. So applications will not be limited by. But as applications push boundaries, they become much more data intensive. For example, they demand more predictability, more speed, more efficiency. Computing platforms will become increasingly strained. And we will see these with various analyses that we will do for different applications in this course. And again, I don't have to tell you again, but machine learning is an example of this today, right? They're pushing boundaries. You could argue that maybe too much boundaries pushing, or maybe too many people are trying to push the same boundary. So the resources are a bit too funneled, but they are pushing boundaries to actually improve LLMs and different, hopefully more machine learning models as well. And they're straining the computing platforms, as we can see, right? Okay, but I think the major realization that we will start with in this course is we're really bottlenecked by memory and storage, for data storage and movement, essentially. Yesterday, you also asked a question saying, what is the difference between memory and storage? And I think I answered it. I'm going to talk about it together in this case. But in this course, our original focus, again, we'll start with data storage systems. So you can see that I actually use the words interchangeably, memory, essentially. And especially, we're going to focus on main memory to begin with, but we're also going to cover the storage, and we'll see the distinctions, etc., later on. But this is really a critical component of all computing systems that we have today. Whatever you design that is executing something interesting, it needs to have some sort of main memory. And this memory system must scale in many dimensions. It needs to get better, basically, in terms of capacity, in terms of technology, in terms of efficiency, cost, and algorithms that we use to manage it, especially if you want to maintain the performance growth and benefits of scaling the technology into the future. I'm going to define these technology scaling a little bit more later on. And if you look at main memory, it's always there, regardless of whatever compute device that you design. There's FPGAs, GPUs, accelerators, whatever, right? I need some water, but I don't know where I put my water. Okay, so that's why we're going to start with the memory and storage focus. And in this first lecture, or second lecture, I'm going to spend some time on discussing why is memory so important, especially today, and give you some data points from essentially a lot of different sources, including some of our research. But I trust my research more than I trust something I read in general, because I try to make sure that it's correct. So you're going to see a lot of our research. And this research is really fundamental in the area. So that's why you're going to see a lot of that also, not just because I trust it, but it's also very fundamental at the same time. Okay, so we're going to see multiple different perspectives on especially main memory to begin with, but I could actually do the same thing for storage, but I'm not going to do that yet. When we cover storage, you will see some of that in some number of lectures. We're going to start with performance, energy, scaling, and robustness. And we're going to also talk about cost, actually. So we're going to see different aspects of why main memory is important. And we're going to also talk about some trends and challenges and opportunities. I'd like to focus especially on challenges and opportunities from these perspectives. Does that sound good? Okay. So let's start with this one. I have this provocative title over here, but you will see what that means later on when time comes. Essentially, today's systems are very processor-centric. You have this chip. This is a processor chip. It could be an accelerator chip. It could be combined. It could be an SoC that has multiple different cores and heterogeneous cores, accelerators, whatever, general purpose accelerators. In today's systems, they all look like this. I'm going to show you pictures later on, actually. This is a picture that I drew in 2008 when I was begging for money from the National Science Foundation to support my research. And they were nice at the time. I don't know if they're nice at this point, but they were nice and they supported my research nicely, because we were arguing these multi-core systems. You need to actually have a scalable memory systems that are predictable, quality of service aware. And this is the nice picture that I still use because the picture is somewhat still the same. Essentially, if you look at this picture, what you see is computation units, right? Cores. And you have seen the design of this in DDCA and FOCA, if you've taken those courses, and hopefully in some other previous computer architecture course that you've taken, because most of those computer architecture courses tend to be focused on the cores. They don't think about the rest of the system, which is really most of the system. So that's where the computation gets done. In fact, inside there's a register file and there's an L1 cache that I don't point out over here. Those are memory structures, register file and cache, L1 cache. Those are memory structures. But the rest of what I describe over here is shared caches, L2 caches, L3 caches, interconnects, which we're going to study later on. This is a, let's say, two-dimensional mesh interconnect over here with some bells and whistles, and memory controllers, and other interconnects that go off chip, and main memory, which looks small here, but it's not really that small, and some other interconnects, and then some storage, and then some other interconnects, and then networking, etc., which we're not going to get out at this point. But this picture is interesting because if you actually do the calculations in a single node, more than 95% of the hardware real estate of a single node is dedicated to data storage and movement units, storing and moving data, right? Sounds good? We're dedicating most of our resources, an overwhelming majority of our resources, hardware resources, to do data storage and movement. Computation is a very small fraction. I'm going to back this up with real pictures. And I started taking the approach of a kid these days, because that's the best way to explain some of these things for people who, in general, don't understand, let's say. If you were a kid, what would you say about this? Okay, kids come in different ages. If you're a 0-year-old kid, you wouldn't understand. If you're a 5-year-old, you may understand, but you don't care. Now, if you're a 10-year-old, and if you're given this picture, and somebody tells you, I'm designing this system, I'm dedicating almost all my resources to storing data, that should not be my bottleneck, right? Or you can phrase the question such as it's less leading. But again, let's just ask that question. And probably that kid intuitively would say, no, you're spending all your resources on this thing. That should not be your bottleneck. And that kid will be honest with you. Right? As people get older, they become less honest. If you tried this with a 5-year-old kid, it's going to be harder. But they will be even more honest, frankly, because they're not yet gone to the primary school, etc., which starts indoctrinating them in some way, where they're supposed to figure out how to behave, right? Conformity is important, and conformity is actually very interesting in psychology, but it's also very dangerous, because as people conform, bad things happen also. So you got to be careful. There's a balance there. Okay, so the kid will tell you that this is a bad design, probably. Think about something else. Basically, why? Because the system is still bottlenecked by memory. I forgot to say that. I kind of got carried away. But basically, the kid would tell you it should not be your bottleneck, but it is still our bottleneck, basically. We're dedicating almost our resource, and it's our bottleneck. This should immediately tell us that we're doing something wrong, maybe. Right? And I strongly believe that we're doing something wrong fundamentally from the very beginning of the computer design. And we're very processor-centric. Nothing else can process the data. As a result, we move the data all over the place, from the storage to memory, caches, other caches, register file, and then it gets processed inside there. And then once you need to write it back, you go through that path again. Right? But it's almost stupid. Sorry. I think I told you that I'm going to take a critical view. This doesn't mean that I'm going to make people happy. I'm just going to take a critical view. And everybody's designing this because it makes money. But at what cost does it come? Okay. So basically, we have a big problem. Computing today is bottlenecked by data, and we're probably not handling that thing very well. I'm going to give you in these lectures many examples of different workloads, but we talked about AI. Important workloads are all data intensive, and they all require rapid and efficient processing of data. And data is really increasing. So this problem will not go away, basically. We're going to be increasingly constrained by data. This problem is much worse compared to 10 years ago. It's much worse compared to 20 years ago. So go back in history. At some point, memory problem was not that important because logic did not scale very well. And as logic scaled, memory became much more of a bigger bottleneck, essentially. So basically, as we want to work on more data, we want to perform more sophisticated analysis on more data, will be more bottlenecked. And again, this is a pictorial view of what has happened to, let's say, AI until some time, machine learning workloads, basically. This is a slide that I borrow from those people who are designing these wafer scale chips. And you've seen this. Essentially, both compute requirements have been growing exponentially, as well as memory requirements have been growing exponentially. You have 4 orders of magnitude increase in memory requirements in just a few years, essentially. And compute requirements also have been increasing similarly. Right? You can argue that this is a crazy way of doing things. Yes, I think everybody should not be doing things, but some people should be trying to do trying to scale these things also, right? It's good to think about that. Yeah. Okay. So we have also analyzed a lot of edge workloads in an edge TPU, which is a much smaller system, especially compared to Cerebras. It's like nothing almost. But basically, at the edge, if you want to do inference and processing, memory also is a big bottleneck. We're going to see some of these results later on, probably next week. I don't think I'll come to that today, but let's see. Actually, I may show you a little bit today, but not the solution. But it's not only machine learning, AI, regardless of some people may try to make you believe. There are many other important workloads, actually. Databases, they're still important, even though they're old. Maybe some people think it's boring, but they're important. We actually deal with a lot of databases in our lives, right? Without knowing, maybe. I wonder what those Python people are thinking about databases. Maybe you can answer that. Okay, graph processing, graph analytics, right? That's also, again, machine learning can be a part of all of these applications, by the way. Machine learning, like in database machine learning, you can do machine learning. So I think I'm not saying AI is not important. AI is very important, but it should not be the only thing people should be focusing on. AI will actually change how we do a lot of these applications also. So graph processing, we're going to talk about some of those later on. In-memory data analytics, different types of cloud computing workloads, for example, and also more general data center workloads, cloud computing. And there are a lot of papers that have been written. Some of these are referenced here. And I cannot keep updating the slide because otherwise I would be doing that only every semester. These are some of the papers that show that memory is a big bottleneck in those workloads. I'm going to show you some more data later on. Some data later on. So we have actually analyzed these workloads that you see on the slide a lot together with Google. I spent one of my sabbaticals in 2016 and took one of my students also over there to Google. And we analyzed a lot of these workloads heavily on real mobile devices. And we tried to understand the data movement bottlenecks in these. We're going to talk about that work also later on. And also TensorFlow is very popular. It's used a lot actually in the world, but we're going to get to that. So in these workloads, for example, we found out that memory is a huge bottleneck in terms of energy and performance. I'm not putting numbers yet, but we're going to get to that. There are other workloads that are really important. For example, genome analysis. You have a genome sequencing machine. One of them may be this big, maybe $1 million or $3 million. We're going to look at also smaller ones. They're all high throughput. And it spits out these ACTGs, which are the bases. And you need to really analyze this genome and figure out what parts of it you should focus on. And that could enable much better treatments, personalized medicine. That could also enable scientific discovery, essentially. And this is actually a field that's really important, in my opinion. We're going to see some of that, again, in these courses. But again, you're very much data bottlenecked over here. You're moving the data out of that sequencing machine and potentially to a data center to do all of these analyses. And if you're really in a life-critical situation, you're trying to save a baby, for example, and if you really want to administer the right drug that is personalized and you want to know the genetic characteristics that would make the, let's say, drug work or not work, then you really need to do this very fast and efficient. So these are actually, they're real medical case studies where people discuss these things, and they really need much faster analyses. Okay, again, in most of these, memory is a big bottleneck. So we're going to talk more about these. And this is another sequencing technology. I don't want to bias you with that huge thing that you cannot buy. But if you're interested in this, you can buy this one. It's only $1,000 or so. And it's true, it's like in your hand. And you can sequence things. In fact, there was a high school student a few years ago who sequenced a fish genome and discovered some interesting things related to that. I don't remember exactly what, but you can see high school students who are actually motivated, who are thinking big, who have a vision, can do interesting things today also. They're not limited by the cost of the previous machine. Well, they need to be at least somewhat wealthy to get this one, which is Yeah, which is still a barrier for most of the world, but still it's not as bad as this one. I'm not going to be able to afford that one. Okay. So, this device is actually a great data generator. It can generate a lot of data. This was used very heavily during COVID times. Many of these were shipped to the Far East to understand the development and the variants in the COVID-19 genome. So this is actually very useful in the field as well. The problem is, it's a great data generator. It's a terrible data analyzer. Where do you do the analysis of the data that comes out of it? Right? You have sequences coming out, and then you need to move it somewhere. A laptop, at least. Usually a laptop is not sufficient, depending on the analysis you do. Then you move to a data center far away. So the use of this portable device is mostly gone at that point. Well, in-field data collection you can do. That's the good part. But in-field analysis is not possible because of the lack of analysis capability. And again, one of the major issues is really memory is a big bottleneck. So we've been analyzing this, for example, for a long number of years. And this is one of the earlier papers that we wrote on this topic. If you're interested, it's still a very good paper to read. Even though tools have developed over time, it's a good example of how to analyze existing workloads in an emerging technology at the time, especially. Okay, so basically the point is memory is a bottleneck. So in this lecture 2, I'm going to take a critical approach to the memory system. We're going to especially look at main memory system, and we're going to look at how it is evolving, how it has evolved and how it's evolving. Basically, there are some recent, not so recent anymore, but it's still recent in the grand scheme of things, because computing history is, let's say, 100 years, right? Electronic computing is maybe less than that, slightly. But still, 100 years is a good approximation, right? And I think memory system has become a whole lot worse, and especially the recent 20 years or so. Because recent technology, architecture, and application trends have led to new requirements from the memory system. And old requirements became exacerbated. And people always demanded a lot from memory. We want higher performance. We want low cost, high capacity. We want low energy, recently especially. Energy has become a recent big concern. But cost was always there. People always wanted high capacity, high capacity, high capacity. And then high performance, high performance, high performance. Performance has multiple aspects, latency and bandwidth. We wanted both in general. And then energy became there. And then other things like quality of service, predictability. Am I getting predictable accesses from memory? Those things started appearing also. So basically, there are more requirements that we have, and we're going to demand even more, as I have hopefully shown you with some examples. So I will argue that the way we design memory and memory controllers today, and I'm going to take a focus on main memory. That's why the memory will be DRAM, dynamic random access memory. I'm going to show you some examples of it. As we design them, are unable to satisfy these requirements, and will be unable to satisfy these requirements. So we need to actually rethink them in a different way. And this course will be about that, at least in the initial 5, 6, 7 lectures or so. And there are also some emerging non-volatile memory technologies that enable new opportunities, like merging of memory and storage, which kind of deals with your question from yesterday. And we're going to look into that, but that will come a little bit later. And this is actually a tough area, because emerging technology is always a tough area, and there should be people working on it. But even emerging technologies that are not so difficult are hard. So I'm going to give you examples. PCM is phase change memory, so we're going to see that. So my group has been doing work on all of these areas, so it's very interesting to see how things have been evolving. Okay, so basically, I think we need to rethink the main memory system, as well as the devices that go into it, and the software that really interacts with it, to fix the issues we're having with memory and enable these emerging technologies while satisfying all of the requirements. So this is kind of a one-slide summary. It's a high level, but now we're going to go into a little bit more depth. Does that sound good? Okay. Okay, so these are the major trends. So I promised we'll cover some major trends. These major trends have not changed, and I'm going to see if there's something that is forgotten, because let's see. So basically, there are 3 major trends, in my opinion. One is we need more from memory, more capacity, more bandwidth, more quality of service, more predictability. Yeah, lower cost, if you want. That's kind of embedded in the main memory capacity, right? We want higher capacity. Hopefully, we don't want much higher cost right? That's important to scale. Already, actually, an existing memory system is more than half the cost of a data center server. In some cases, more than 60–70% of the cost of a data center server. So people are building these data centers. Most of the cost is really main memory because they need huge memories, right? The processor, even though it's an expensive component, it's not accounting for most of the cost. Memory is a cheaper component because of the mindset that we have. We're very processor-centric, right? Processor can process things. Memory cannot process things. But people need so much memory that the cost of memory still dominates the data center cost. So it's good to think about that, right? And if you actually keep scaling like this, more than 90% of the cost will be main memory in a data center 5 years down the road. This is a real problem. We were saying this for many years. Now the industry is saying it. And they come to us, how do we solve this problem? So it's good to think about that. And also, it's good to be ahead of industry. I think I like that. If you're too close to what industry is doing, maybe you should be rethinking what you're doing. In my opinion, this is very good advice. Okay, so I digressed, but it's really related to this need for main memory capacity, bandwidth, and quality of service. And then the second thing is main memory energy and power is a key system design concern. It's been for a while, but it's becoming much worse, basically. And I'll give you some numbers. Again, depending on the workload, etc., more than 90% of the energy may be spent on main memory today, especially in large-scale machine learning, for example. And on top of this, memory is not scaling very well, especially the DRAM technology currently, which is the main memory technology that we have today. It was invented in the 1960s by Bob Denard, who was a very smart inventor at IBM. He also came up with Denard scaling, which is really a fundamental law of how essentially voltage scales, etc., and performance scales with that. But anyway, I'm not going to go into that now. But essentially, it's been very successful, but unfortunately, it's becoming much more difficult to pack more cells in a given area without running into a lot of reliability, robustness, latency, etc. issues, energy issues. And this would have been okay if we had an alternative technology that could replace DRAM potentially, right? But unfortunately, we don't have that technology today. The characteristics of DRAM are so good, and we will see some of those characteristics, that it's very hard to find another technology that could replace it. But people should really push forward with that, I think. That's why I think there should be a lot more work on emerging memory technologies to figure out, can we somehow replace DRAM? And also DRAM is evolving into the future, so maybe we won't have to replace DRAM completely, but kind of fudge it or evolve it with some, I don't know, maybe ferroelectric type of technology so that it can scale better into the future. But again, maybe we'll talk about that when we get to emerging technologies. So these are the three major trends. Now let's go into each of them in a little bit more depth. Essentially, why do we need more capacity, bandwidth, quality of service? Essentially, we have much more data-intensive applications. When I made this slide in 2008, machine learning was not there. Now I can use machine learning as another data-intensive application over here because nobody cared about machine learning. I did care about machine learning at that time, actually. We're going to see some work where we actually tried to use reinforcement learning to design memory controllers using machine learning to actually do better algorithms inside the hardware. Okay, but basically, we have a lot more data-intensive applications. And we have many core systems. I call everything multi-core, but essentially multi-accelerator systems, increasing number of cores and agents that are demanding things from memory. And we want to consolidate more, essentially. In cloud computing, for example, if you want to efficiently utilize resources, you want to put many applications together on a single node. And even in my computer, in the back of my pocket over here, I want many applications running concurrently so that I can get more work done, right? If you think about it. So that consolidation puts a lot more pressure on bandwidth, capacity, as well as quality of service, like predictability. What kind of predictable latency would you get? Would each application get its own predictable performance, right? It's good to think about that. Are there any other reasons for memory capacity, bandwidth, and quality of service becoming worse? Or the need for it increasing? Am I missing anything? Good to think about that. If you come up with it, let me know. Okay. So this is an example slide that shows the capacity gap, as these folks called it. Main memory capacity gap. And these folks are folks from HP Labs at the University of Michigan. They had a nice ISCA 2009 paper. Somebody needs to repeat the study, but I think the trend is similar. At the time, they plotted the core counts that they see in real processors, and they plotted the DRAM memory module capacity. And this is kind of the curve that they came up with. And they basically said there's a disparity in these curves, meaning core count is doubling approximately every 2 years because we can put more cores. We can still put more cores, actually. And memory capacity is doubling approximately every 3 years, which means that we're going to have a much bigger memory capacity bottleneck, because if we keep putting more cores, they're not going to get as much memory. Right? So memory capacity per core is expected to drop by 30% every 2 years, according to their calculations. Does that make sense? So this is not good, because if the software is designed to need more memory capacity per thread, you're getting less memory capacity per thread. That's not good, basically, for how people design software. In general, people design software to use more memory because it's free, right? Python folks, they don't care. What is memory, right? They don't even know memory. So that's the thing, basically. That gives you an idea, basically. People who design software don't care in the end. But this is a problem, basically. And over time, core counts stop doubling at the same pace. What people started doing is they added more caches, much bigger caches. And they tried to reduce the core count doubling. So I don't think this curve is as much, but if you look at GPUs, for example, the core count is actually increasing quite fast. So it depends on what you look at. Again, I didn't do this analysis recently, but if you're an aspiring computer architecture student who wants to do research, it's always good to analyze trends. One thing you can do is analyze trends, what's going on, and that could actually enable you to think about new opportunities for research. Okay, so that's a nice paper. But basically, trends are much worse for memory bandwidth per core. We just looked at capacity over here. Now let's look at a lot of these things. This is a fun slide. We have an updated version, but I like using this old version also. I'll show you the updated version also. So we're going to look at improvement in log scale in DRAM chip capacity, bandwidth, and latency. Capacity is gigabits, for example. Well, clearly it was not gigabits over here in 1999. Today we're in gigabits, 16, 32 gigabits. Well, that's not today, 2017. But this is from a paper that we wrote in 2017. That's why it ends at 2017. Basically, I'll give you this one. The DRAM capacity has been improving constantly because this is the design metric that memory designers design memory with. It's been increasing, as you can see, in the course of these 18 years, it's increased by 128x. It's a large number, right? And memory bandwidth, this is DDR. This is not high bandwidth memory. Memory bandwidth has been increasing, but not at the same level. It's about 20x, as you can see over here, due to improvements in signaling technology, and also bank level parallelism, etc. But this is not 3D stacked memories, which we're going to talk about later. So that actually increases the bandwidth more. So the reason capacity has increased much higher is because capacity is easier to increase. You reduce the size of the cell, especially if you don't care about the robustness of the cell, you keep reducing the size, right? That sounds good. Doesn't matter if the cell works or not. No, that's a bit too extreme, perhaps. But maybe you don't really fully understand whether the cell works or not, and you keep reducing the size. And that's easy to do, actually, in general. Not easy, not terribly easy, but it's a bit easier and cheaper than increasing the bandwidth. That's why you see these curves. It's cheaper than increasing the bandwidth, because how do you increase bandwidth, right? You have a DRAM chip. If you want to get data faster out of it, like at a higher rate, let's say, I don't know, I want to improve the gigabytes per second that I get. You can increase the frequency of the bus. This is already an extremely high frequency bus, it turns out. It's one of the most difficult buses that you can design in a computing system, actually, the DDR bus or HBM bus today. Because everything else, like if you look at networking, etc., the frequency of it is much lower. So it's good to think about that. So it's already the highest frequency thing that we're designing as an interconnect between processor and memory. You want to increase frequencies. So what do you need to do? You need to invent new signaling techniques, for example. You need to invent better data encoding techniques, etc. Maybe compression techniques. That also helps with bandwidth potentially, but then it adds some overheads. You want to invent maybe certainly better interconnects in the end. Right? Not so easy. That's one way of increasing. The other way of increasing bandwidth is adding more buses. Right? You put more pins on the DRAM chip, and you transfer things in more parallel. Now, you could do that without increasing frequency, or you could do it while increasing frequency. But this also adds more cost because, in general, chips are pin limited. Meaning, whenever you design a chip, you already have a lot of pins on the chip. Trying to add more pins will increase your cost because you may not have enough area to add more pins. And if you don't have enough area, you have a bigger chip now. Right? And when you have a bigger chip, you need to potentially redesign a lot of things in your chip to make use of that area. Or if you have space, let's say, magically, for one of those pins, adding more and more pins is expensive still because it's another I/O. It increases your energy, etc. So bandwidth, clearly, adding higher bandwidth increases your cost as well as energy and potentially area. So in the end, you can buy more bandwidth. You can make this curve much better, but it comes at a higher cost and energy. And that's what has happened with HBM, for example. If you compare DDR and HBM, HBM is higher cost, higher energy. Right? And that's what NVIDIA is selling you, a lot of HBM. Even though their GPUs may not be working very well, their HBM is working quite well because their GPUs need that HBM, high bandwidth memory, because of the workloads, right? Because of this thing that we have talked about, data-intensive applications, essentially. Okay, so there's a reason for this curve because it's costly, and the main design decision in main memory is really capacity and cost as opposed to bandwidth. More recently, high bandwidth memory has become the norm, especially in applications that need it, which is good. So that's actually a little bit different, but it comes at a cost in the end. And it goes against the capacity also. If you look at high bandwidth memory, the capacity of it is much lower than DDR because it's 3D stack technology, right? You stack memory on top of each other so that you can actually send a lot of data through interconnects that these different stacks layers share. Okay, so I went into a lot of depth, but we're going to go into more depth with some pictures later on. What do you think latency looks like? That's the other curve over here. Anybody? It should decrease. By how much? In the 18 years that we're looking at over here. These are real data sheet numbers, by the way. These are real numbers that are plotted by looking at real DRAM chips that are designed on average, which average is very good. The distribution is not very wide in DRAM. 15 times. So it's reduced by 15 times. Any other takers? Same as the bandwidth. 20 times, okay. Any other takers? You can do an auction of latency. I'll give you a DRAM chip with that much lower latency. I guarantee you that. Assuming you're right. Which means you're not going to get anything because it doesn't exist. Okay, no other takers, even though I gave you a big hint. 0, okay, you changed your mind. Good approximation. 30% basically. Yeah, it decreased. No, this is decreased, improvement basically. It decreased by 30%. That's the average latency calculated in some way. Some latencies have actually increased. So basically, latency did not decrease that much. And why is that? Well, there are multiple reasons for it. One is fundamentally, latency is harder to reduce. If you want to reduce latency, you really need to do something more innovative, more creative, and we're going to see methods for that. Because you cannot just reduce the size of the cell. Right? Even though that's hard to reduce, especially at small technologies, that's still easier to reduce than latency, right? The size of the cell. Bandwidth, again, you can pay a lot of cost. Latency, even if you pay a lot of cost, there's a limit to how you can improve it, actually. And we're going to see that. Okay. So that's one of the reasons. Fundamentally, latency is much harder to improve than bandwidth, and bandwidth is harder to improve than capacity. But then there's another reason, which is more mindset and business reasons, which is DRAM chips are mainly designed for improving capacity or reducing cost cost per bit. That's the main metric that the manufacturer is optimized for. It's not necessarily a good thing to do, but that's what people have been optimizing for. So as a result, the other metrics are not as important, right? So if you're not trying to optimize latency, clearly latency is not going to be optimized. This is, again, self-fulfilling prophecy or goal. This is also a business model issue, I would say, because of this mindset, it's not clear whether these manufacturers, this business knows how to sell chips that have lower latency. It's good to think about that because this is actually a real issue. And if you are an entrepreneur, you want to get into a market, you should always consider this. No question about that, right? Yeah, do I know how to sell? Even if I improve latency, let's say by 2x, which is going to be huge compared to 1.3x, can I sell this? Can I make money? Do I have the business model? Or have I put myself into a corner over 50 years by optimizing capacity and never selling latency? There's also history associated with these things, right? So it's good to think about that. So there are multiple issues. One is really fundamental. Scientifically, this is harder to improve. But the other is, in my opinion, not so fundamental, but still important. It's very human, business related and mindset related. Okay. So this is a bigger perspective of it. It's from one of my PhD students, Minesh Patel. He's an assistant professor at Rutgers University in New Jersey right now. He did this huge analysis of the, okay, yeah, go ahead. Okay, sure. Yeah, that's very good. Essentially through parallelism, right? Parallelism. Yeah. We're going to look at that, but essentially you can improve throughput. You can basically transfer more bytes per second, but the latency may actually increase. So let me give you an example. Pipelining, for example. When you pipeline an operation, an instruction, for example, takes 1,000 nanoseconds, let's say. When you pipeline it, you divide the pipeline stage, let's say, perfectly. Each stage, let's say a 5-stage, because 5-stage MIPS is the best processor ever, right? Each stage is 200 nanoseconds, let's say. So ideally, the latency of that instruction will be 1,000 nanoseconds because it's going through these pipeline stages: fetch, decode, execute, memory, write back, right? Ideally, it's 1,000 nanoseconds, but pipelining adds overheads because you have latches. Let's give it 200 nanoseconds, 1,200 nanoseconds, the execution of that instruction. So your latency increased, but your throughput in terms of instructions per second has reduced, assuming you can keep the pipeline full. Now you're finishing one instruction every 200 nanoseconds, plus the additional overhead, let's say, right? So that's a very good example between how you can actually improve throughput, but increase latency. Make sense? So they do a lot of pipelining, for example, on the bus. And they do a lot of parallelism internally. And they do increase frequency, which helps with latency. But the overheads of the other things they do is much higher. That's a very good question. It's good to discuss this bandwidth and parallelism, or throughput. Bandwidth and latency, or throughput and latency disparity. Ideally, we would like to improve both. Yeah. Okay. Let me give you a couple more data points, and then we're going to take a break. But this is a more recent study that we did in 2024, which covers a lot of things about actually DRAM. I'm going to mention the paper. These are the links to the paper, actually. This is also all public data. We did a study of the 54 years of DRAM, and we looked at a lot of data sheets. I don't remember how many. It's in the appendix of this paper. But this basically shows that capacity has improved greatly since 1970. 1970s, I should say, because the first DRAM chip was manufactured by Intel in 1971, Intel 1103. And Intel decided to quit the memory business. Maybe it shouldn't have. It became a processor company. It should have stayed as a processor plus memory company, maybe. Maybe they wouldn't be dead by now. Almost dead, at least. But anyway, so capacity has improved by more than 1,000,000x, as you can see, over the course of 54 years, or 50 plus years. And this is the latency compared to capacity. These are different latency parameters in DRAM, which you will get to know in later lectures. We don't need to go into the details right now. But TRC is the row cycling latency, how quickly you can open a row and then close it and open another row, basically activate 2 rows consecutively. So you can see that that latency has been reducing, but this is the timing axis. Timing axis doesn't look as nice as the capacity axis, as you can see. That's kilobit or kibibyte, sorry. But you can see that the capacity has improved, latency has improved for some time, but it's almost flat in the recent years, right? So maybe people have run out of ideas also to improve latency. It's good to think about it that way. Or maybe the cost of improving latency has become too much as well, right? Okay, so that improvement is 8x if you look at 54 years. Still not comparable to a million X. It's good to do these studies. I would recommend people to do this sort of studies if you're trying to get into an area, because this also gives you a bigger picture and enables you to focus on big things, right? So why didn't this improve, for example? Why don't we improve this? Is it beneficial to improve it? What applications would benefit? It's always good to ask these questions. And there are applications that would benefit from latency improvements. We're going to talk about memory latency later on, because I think this is a critical area that is not as much recognized. Okay, and you can see this is the more recent years. Actually, capacity improvements have also been relatively reducing, as you can see, right? The shape of the curve is becoming, the slope of the curve is lower. But latency improvements have certainly been flattening, and some latencies are increasing. Okay, and we're going to see later issues like RowHammer increasing latencies in different ways. Okay, so this is probably a good time to take a break, because I've kept you for some time. Let's take a break until 2:40, and then we're going to continue our exploration of issues in memory. Okay, let's continue. Is everything good? Turned on? Okay. Okay, so I'm going to do a context switch so that we could cover this one. Otherwise, I'll talk about memory forever. We're going to cover course info and logistics relatively quickly. If you have any questions, this is your time to ask. We've already had this introduction. If you have any questions, you know how to contact me. But again, you know that you should probably email multiple times. And we already introduced Mohammed, who's here, as you can see, and Konstantina, who's escaped to the back. This is the teaching team. You know the instructors, Konstantina. Okay, who else is here in the teaching assistants? Let's see. I see Arsh, Andreas, Evo, Susanna, Maria, Konstantinos, and Jihan. Okay, that's better. Is that all? Is someone hiding? I thought I saw Seguras earlier. Let's see. That's him. Get a conflict. Okay. What? He was here, right? Yeah. Yeah. Okay, so I have a great team of teaching assistants, and I would suggest getting to know them. They're all part of my group at different stages in their, let's say, research experience. And I would suggest getting to know them and their research. They're all doing research. Some of them are going to deliver lectures. Some of them are going to deliver lectures that are part of the course. Some of them are going to deliver lectures on cutting-edge research that they have done. So normally in this course, we have a few cutting-edge research lectures where you get to know, let's say, 5 or 6 papers on a topic during the lecture. It's like a conference presentation. So that's your opportunity to ask them questions if they're not delivering some other lecture. And this is also good because you get to know some real cutting-edge research that is published maybe a few days ago, or that's going to be published maybe a month later. Okay. There are 2 more who are coming over here. Late coming teaching assistants, Mayanka and Harshita. Don't hide. Okay. Okay. And getting to know them is nice because especially if you're interested in doing, clearly you're going to interact with them in the labs, homeworks, etc. Hopefully nicely. But if you're interested in doing research in this area, they could potentially provide you with potential research topics, and they could be your future mentors. It's good to think about that. Okay, so these are some of the goals of this course. We've covered this a lot, so I'm not going to go over this in detail again, but our goal is to really understand and evaluate trade-offs, especially new ideas, understand how decisions made, ideas affect both the high-level programmer as well as the low-level hardware, thinking critically, that's probably the most important part, thinking broadly across the levels of transformation, because ideas have implications across many different parts of the computing stack, and it's good to think about that. Even things like business models, we're going to talk about that, right? I think that's really important to consider broadly, essentially, and understand how to analyze and make trade-offs in design, and hopefully applies the above in some lab projects and homeworks. Clearly, lab projects are going to be very limited in terms of what we can do. And I said yesterday that we need to revamp the labs at some point, but we have not done it yet, unfortunately. So you'll have to suffer through the old labs, which is not bad, I think, but it's maybe too easy. Maybe you'll not feel that way, but I feel that way. Okay. Okay, and then there's homeworks, of course, that is where you'll apply things, hopefully. And then there's also reviews, which is not here. I think you will apply, especially in the reviews, paper reviews. We should update the slide with reviews at the end. Okay, so I think I've said a lot of these things, but I'll emphasize principles and trade-offs. We're going to look at that. We're going to see a lot of precedents, meaning how people have done things. We're kind of doing that today. And because if you understand the precedents, you can develop better things, right? And precedent doesn't mean it's good. Precedent means what comes before, right? Precedent, it comes before. It doesn't mean it's good. It may not be a good design necessarily. So it's good to think about how to develop better designs. And that comes from understanding the principles and evaluating trade-offs of different designs and ideas, and applying principles to the domains that you're trying to develop systems for. And hopefully you can develop novel out-of-the-box designs, right? That's my goal, basically. I think everybody who takes this course should critically question things, and at the end should be able to critically question things. I think that's a human, let's say, element that all of us have, but maybe it should be nurtured more in educational systems that we have in the world, as opposed to kind of destroyed for conformity reasons. But I think in this course, we don't want that. We want critical thinking. And hopefully that will enable you to develop better designs into the future. And it's a good skill to have because you can make money out of it. That's one reason. Or you can have a positive impact on the world. Okay, I've already said this. And we're going to focus on computer architecture clearly, but we're going to look at adjacent areas too. Okay, in the end, I think regardless of your future direction, this is a master's course. So your future direction probably is computer engineering. Who knows? We don't know. But we don't know what the future brings. Even though you may think it's computer engineering, you may become something else in the future. But hopefully, regardless of your future direction, I think learning the mindsets, the principles, and the methodical trade-off analysis techniques we will cover will be useful for many things. You can design better hardware, better software, better systems, make better trade-offs in design, maybe help you understand why computers behave the way they do. You improve frequency and you never get higher performance. Well, why? Because you're not targeting the right bottleneck, right? Memory is your bottleneck and you're improving processor frequency, wasting a lot of power for no reason. Good to think about it. That's my view of, that's my overall view of things, right? And hopefully solve problems better. That's more general skill than targeted for computing. Think in parallel. That's also a very useful life skill, I think. A lot of high throughput, low latency thinking. And think critically. Essentially question and analyze everything honestly and scientifically. And we need both of those, scientific analyses and honest analysis. I think they go well together, right? A 10-year-old kid could be honest, but may not be scientific yet. Okay. Let's see. I think this may seem like computer architecture may seem like computer hardware. And I get this from some students sometimes. This is like electrical engineering. But it's not really. Computer architecture is really at the interface. And the way we define computer architecture, it's really across the stack, right? So this is really across the stack, I would say. We'll, of course, cover a lot of hardware, but we'll also cover a lot of high-level implications on software. So essentially, you can develop better software if you understand the hardware. You can design better hardware if you understand the software. I just said this earlier in a different way, clearly. And in the end, I think what really is important, in my opinion, is designing a better computing system. Because hardware and software are things that are fungible concepts, in my opinion. You can design hardware and you can minimize the software, meaning you can directly execute programs inside the hardware, right? You can think of it that way. So your hardware can be very complex, but with a lot of resources, you can directly execute a lot of programs in hardware. So where you draw the line between hardware and software should be something part of the trade-off space that you're thinking of, right? Hopefully that makes sense. Okay, but basically, hopefully you'll understand both better here. And again, we're going to cover both hardware and software. Okay, required background. This is good to think about. Digital circuits course, I said over here, programming. I think you need both in the end. And ideally, you would take digital design and computer architecture because we have a specific way of teaching that course, which I believe in, DDCA essentially, which I mentioned last time. An open mind willing to take in many exciting concepts, So open mind is also important. Again, hopefully you have the required background. Otherwise, you may need to put out extra work. Good to think about that. So hopefully you learn the material thoroughly. And we're going to cover a lot of things. And the key takeaways are the most important ones. As I said, key ideas, key trade-offs, right? The details of implementation, that's something that's a little bit less important, but it may become important when we actually describe things. So nitty-gritty may or may not be important depending on things, but having the ability to do the high-level trade-offs is more important, at least for this course. So how do you do that? I would say attend the lectures, do the readings, do the exercise, do the labs, do everything basically, as any good instructor would say. Yeah. But hopefully you will also question things and ask questions. Right? I think it'll be a hard but fun and informative course. That's my experience. Those are the things that people who really like the course would say. Ask questions. I think that's important. Challenge assumptions. Take notes. Participate. I think that's some things that we value, and we have a good environment for enabling that over here. So don't be shy, essentially. I think performing the assigned readings is useful because we're not going to cover readings in a lot of detail in lectures. We're going to give you high-level concepts and ideas, trade-offs, etc. But for example, if you want to learn more about a particular work, you got to go and do some reading, right? We don't have any textbooks for this course because no textbook incorporates the materials that we cover. Some of it, yes, but a lot of it is so cutting edge, yet still so fundamental. But there are no textbooks that are written on the topic. Or memory-centric computing, for example, there's no textbook. But I'll recommend you our almost 100-page archive paper that talks about memory-centric computing. We'll turn it into a textbook at some point as we organize things, but it's not a textbook yet. Right? So there will be papers that we assign. Again, you don't have to do all of those readings because it could be a lot also, but there will be some homework assignments for some critical readings that we require you to do. Of course, require in quotation marks, because you can, those are the things that we recommend you to do. If you don't do that, then you won't get the credit for those in the homeworks, of course. But hopefully it'll be fun. So participating online is important. Lecture is good. Zoom is okay if people are attending. Do we have Moodle? Okay, we have Moodle. Do people participate on Moodle? Okay, I see. Do people make use of it in classes usually? Moodle? Who makes use of Moodle? Okay, I see only a few hands. Who doesn't make use of Moodle? Be honest, it's okay. Who doesn't care? Okay, some people don't care. I don't see a lot of love for Moodle flowing in this room. In fact, I don't love Moodle, frankly. It's terrible, in my opinion. The interface is so bad that I don't want to even go into and log into Moodle. There you go. I don't know who designs these things, but certainly they don't consult professors when they design these things. You can see that the communication problem exists everywhere in life, right? I'm the person who actually can make use of Moodle and can provide good feedback, but there's some design that happens, and even if you give them feedback, it doesn't work very well. Okay. And I'm too busy to design Moodle. I'm not going to do it myself, right? Okay. Yeah, so participate as much as you can. Lecture is fine, no problem. Start early as much as you can because it's going to be a fast-paced course in terms of assignments. They will keep coming essentially. And if you want feedback, come to office hours. And remember this quote that I gave you yesterday from Pasteur: chance favors a prepared mind. And he's looking sternly at you. Don't think you'll get lucky, basically. Prepare. Okay, it's fun to also teach this course, as you can see. So basically, I think it's going to be fun. If you have the mindset that you're going to have fun, you're going to learn a lot, and you don't really care about your grade, or if you care about your grade, you're going to figure out how to get that grade, because there are a lot of opportunities to get that grade in this course, unlike many courses, because you can have a lot of extra credit assignments, as I discussed yesterday, right? You may not be a good exam taker. You may be sitting there crying during the exam and doing nothing, but then you can do something else much better, and you can exploit that, right? So in the end, how you prepare or manage your time is very important. And this is a master's level course. You're not babies like freshmen we teach in DDCA. They're not babies also, actually, but sometimes they act like babies. Anyway, sometimes old people act like babies also. Humans are like babies all the time. But basically, take responsibility for how you do things in this course. That's my message over here. There will be assignments, clearly, lab, homework. They will take time. Start early, work hard, and know your strengths and weaknesses, like Richard Hamming said, right? If you know your strengths and weaknesses, then you don't waste time on inefficient things, and you can learn the most efficiently. And it'll be a heavy course, as I said, but hopefully it'll be worth it. You'll learn a lot of fascinating topics and understand how to do trade-offs. Okay, and it will hopefully change things on how you think about different things as well, right? Not just computing platforms, but it will hopefully enable you to critically examine a lot of things. We just critically examined Moodle, for example, for a short time. We could go deeper, but well, probably it's a waste of time to go deeper on that topic, at least at the moment. Okay, so this is the evaluation because the university requires us to give grades, which is also debatable whether that's a good thing or not. But since we're required to give grades, we have to do it. This is correct, right? Okay, this is how you'll be evaluated. There are lab assignments, 50%. There's a final exam, 30%, and there are homeworks, 20%. And homeworks include the paper reviews as well. But there will be so many optional potential paper reviews that you can actually easily double that homeworks to 40% or so, right? Is that true? You've taken this course last time. Yeah. And you've done a lot of paper reviews. Yeah. And he's developing a lot of ideas because he did a lot of paper reviews. Yeah. So that's it, basically. It's very simple, actually. Lab assignments are important. And we haven't revamped them, so they're easy. From my perspective. Difficult is in the eye of the beholder, right? Whoever does things. For you, it may be difficult, but hopefully you'll conquer it and it'll be easy at some point, right? Okay. Any questions here? Yes. Oh, okay. Well, I don't remember that. Do you remember? What's the highest percentage? Somebody. Okay, that's good. Yeah, yeah. Yeah, some people did really a lot of extra credit. You can get extra credit on labs also. Or even on the final, actually. There are extra credit bonus questions we have. Yeah. Yeah, so there are extra credit opportunities and everything. Yeah. In my opinion, the grade is easy to get in this course, Frank. I've never had a course like this. I wish I did. So grade should not be your concern. You just need to know how to get that grade, right? If you are not a good exam taker and you focus on the exam and you ignore everything else, maybe you're not going to get the grade you want. Right? If you're a terrible programmer, which I wouldn't recommend you to be, and you're not going to finish any of the lab assignments, you can focus on the other ones. So this is, of course, extreme cases that I'm highlighting. So in the end, it depends on you, not me, to give you the grade. You get the grade. That sounds like a great university environment to me, within the constraints that we have that are dictated to us. What do you guys think? Konstantinos agrees, I think. He's taken some courses. Did you ever take this course? No, okay. Maybe it's time. Okay. He's finishing his PhD next year, so yeah, I don't think he wants to take any other course. He's going to teach this course at some point, maybe. Maybe a better version of it. Okay. Okay. So I already said all of this, many extra credit possibilities. Okay, course website is here. All slides, lecture videos, readings, assignments are to be posted. Plus, there's a lot of information. I would suggest checking it frequently. I mean, clearly we have the lectures on YouTube, so you can watch them anytime you want. Hopefully, you'll still attend the lectures because I think it's more fun here, unless you have a huge screen TV and you want to drink your beer or wine and whatever, right? That's a different environment. But then you cannot ask questions. Okay. So office hours. There will be office hours. These are online. You'll get Zoom link. And this is the time. Is that finalized this time? Okay. Yeah, if you have any questions about logistics, assignments, please attend the office hours. Don't expect the TAs to do the work for you. You can certainly ask questions, but they're not going to solve your, let's say, they're not going to provide the solutions for you. And I would suggest trying to debug things yourself first before coming up with a lot of debugging exercises for the TAs. The TA's job is not debugging things for you. Debugging is part of the assignments. Debugging today is actually very easy, right? There's a lot of online resources for debugging. Even ChatGPT can do a lot for you. I don't know. We need to consider things with ChatGPT in the future, but Don't cheat, basically. Okay. Lab session. So there will be guidance and support for the lab assignments. This is the time, Tuesday, 17 to 18, starting next week. Yeah, next Tuesday. This is hybrid on ETZ H71, which is like a classroom that looks like that. And you can also join online. Does that sound good? Any questions? Okay. So there's a homework that's due, which is an easy homework, probably the easiest homework, where you would provide information about yourself. But you have to provide this so that we get to know you a little bit, since you got to know us. It's only fair that we get to know you just a little bit before we start getting to know you more. So please submit it. This is submitted to be on Moodle, right? Okay, so the assignment says that. Okay, so somebody asked that question earlier. So all assignments are going to be submitted on Moodle. Lab 1 is already out. It's due October 10th. And homework 1 will be out soon. It's going to be due in 2 weeks after its release. And again, all assignments and announcements will be here. And labs can be done anytime until the end of the semester. So I'm going to give you, sounds like a perfect course to get grades in. Not many people do that. They're very strict in time. But I don't want to do that. My goal is to really enable your learning and growth. So if you can actually do the lab, have time later on, you can do the lab later. Right. Reviews also, yes, reviews also. That's true for reviews. But you have something else to add. Can you press the button here? Okay, this doesn't work. Go ahead. Yeah. I see. Or you're not guaranteed to get feedback. Some people can be nice as Konstantina and give you feedback still, but don't abuse it. So basically, they have to provide a solution by the deadline, right? So that they can get feedback. Yeah. Okay. Does that sound fair? Okay, unless if it's going to open a can of worms. No. Is it going to open a can of worms? Okay, say it quickly, and then maybe I'll close the can of worms. It opens it up. Yeah. Okay, go ahead. Yeah. Mhm. Yeah. Yeah. Mhm. Yeah. Yeah. Okay. Yeah, that's good advice. That's a nice way of saying we'll catch people who use LLMs. I know. Yeah, yeah. Yeah, yeah. Yeah. If you're going to use it, make it so good that we're fooled that you're not using an LLM, which is very hard to do. Okay. But then that requires you to understand things better. Yeah. Okay. Any questions on this? Yeah. Okay. So yeah, this is another required reading. Is this part of the homework? Okay, that's good. We've talked about this last time, so I'm not going to go through this again. You can use an LLM, but you won't learn much if you use it. Okay. I've already gone through some of the important parts, but there's a lot in that paper that actually I agree with in terms of how to approach things with a critical mindset and how to do research. So I definitely recommend reading this. And it's written by someone who is really revolutionized how things are done, right? Error correcting codes, etc. So keep that in mind. Okay, there's also more talks that I would recommend to you, but I'm not going to go through these. And that's the end of logistics and course info. Any questions? Yes. Okay, where do they submit the Hamming report? Yeah. So it'll be defined when you get homework 1. So it's required right now, but there's no mechanism for you to submit yet. Or you can prefetch by reading. How many people have already read it? Oh, there you go. That's good. Did you read it as part of some other course or? Okay, that's good. That's good to see. Yeah. Good. We'll have fun in this course. I didn't expect any hands, by the way. But yeah, maybe that's not DDCA. Sorry. Good that you're doing this because I don't want to do this mess to make it work. Yeah, go back. Back. Yeah, okay. This was, yeah. Well, yeah, okay. That's okay. Don't worry. Okay, any other questions on logistics? No, everything answered, everything clear. Again, I will emphasize my goal is to enable you to learn. In the end, I cannot push things into your head to learn, and that's not my goal either, right? That reminds me of things I read during my middle school. Charles Dickens. How many people know Charles Dickens? Okay, that's good. Yeah, yeah. He had some views on education, like how to how education should not be done. Basically, it's not, children are not vessels that are to be filled. Right, that's what he was saying. Pupils are not vessels to be filled, and I agree with that. Basically, it's more like you should be ready to get things out, and we provide the opportunity for you to get things out. So basically, there's a lot of learning opportunity over here, and what Konstantinos mentioned earlier jives well with this one, right? You can do things to get the grade, but then learn nothing potentially. But I wouldn't recommend that in the end. Okay, and maybe you're not going to get the grade anyway, because there will be smart people like Konstantinos who will figure out, oh, this is an LLM. Let me ask you some hard questions to figure out whether you wrote that one or not, right? Does that sound good? Yeah. Well, let's see about that. Okay. Okay, basically memory is critical for performance. So we context switch again. So you can see that context switch is fundamentally a problem with single core systems. I'm a single core. I can deliver only one stream of lecture, and we had to switch to another thread. If you had a copy of me, you could be hearing both this lecture and the other lecture. So it's good to think about this interrupt or context switch. Interrupt is a very archaic concept, in my opinion, that is really archaic to single thread of processing. If you are multi-threading and data flow, interrupts are very natural to be handled by some data flow graph or multi-thread that's actually ready to handle it. Anyway, I had to go to that aside because you may have learned about interrupts in DDCA especially, but there's a different way of doing them. Okay, so memory is really critical for performance, and latency is important for some of that performance. So latency, bandwidth, capacity, a lot of these workloads are bottlenecked at different parts in different metrics related to memory. And we're going to see some numbers now. So let's jump into some numbers. How many people know this name, Dick Seitz or Richard Seitz? No one yet? Okay, you'll learn now. So Dick Seitz was a chief architect at Alpha. How many people know Alpha processors? Digital Equipment Corporation. No, nothing? That's because they're dead, probably. And they are dead, actually, because Digital Equipment was a major innovator in computing system design. They designed the PDP architecture, I think personal data processor, and then VAX, terrible naming, virtual address extensions, one of the most complicated ISAs in the world. And then later the Alpha ISA, which is one of the beautiful ISAs in the world. And they actually built some of the fastest machines at the time. They were competitors with Intel for many years. And then they died. They were bought by Compaq, and then they kind of over time dissolved. So they're not making any machines anymore. And I don't think anybody's making any Alpha machines anymore. But Alpha is an ISA. And Dick Seitz was the chief architect of many Alpha processors over many years. You can see from 1988. And they designed some of the fastest processors of its time, like Alpha 21264 was 500 megahertz, much earlier, much faster than Intel processors at the time. Anyway, he wrote this article. It's the memory stupid, which sounds aggressive, but it's not that aggressive because it's inspired by a politician who ran for the US president around the same time. You can guess who that is. And his slogan was, "It's the economy, stupid." And this is kind of saying, it's all about the economy. If we fix the economy, and I'm going to fix the economy, so I should be the president, right? Here, he's saying that it's all about memory in the end. And this person, Dick Seitz, who has dedicated a lot of his life in processor design. He was designing processors in order, out of order, etc. And in this design, he wrote this one-page paper. It's a one-page paper, actually, after they designed a flagship processor, which they thought would be the fastest processor, and it was actually the fastest processor. But he reflected on it, and he basically said, we designed this processor to finish 4 instructions every clock cycle, which is a fast clock cycle. But it's finishing 1 instruction every 4.7 clock cycles on this important database workload, which we thought we designed this processor for. So the processor can finish 4 instructions, but it's finishing 1 instruction every 5 clock cycles. It's operating at about 5% of its peak throughput, essentially. And basically, they analyzed the reasons, and they found out that the processor is waiting for memory for most of the time. Its caches are useless. It's waiting for memory. And you can read this. I kind of summarized the one-page paper with some stories. And he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And you can see that it's pretty strong, only, in emphasis. I kind of agree with them. So you can see where we're coming from, right? This is 1996, and they have lofty goals, but they cannot achieve those goals very well because memory is a big bottleneck. Make sense? Okay, so that's one example. I'll give you a bunch of data points. I can give you more, but we don't have time to give a lot. This is my own PhD thesis. This is the first, actually, it went into my PhD thesis, but it was done before my PhD thesis was done. This is the first paper that I wrote. I did an internship at Intel, and then we started working together. And we analyzed all of the workloads that they have in their arsenal to design the microprocessors at the time, and tried to analyze the bottlenecks. And we found out that most of the time, the processor is waiting for cache misses on average across 150 workloads or so. That's a lot of workloads. Not all workloads, but we looked at the memory-intensive ones especially. That's a lot of workloads, and it's essentially waiting for cache misses to come back from memory. At that time, L2 caches were the biggest caches and the last level caches in these processors. Okay, so the processor is really not stalling for about 30% of the time. Right? Not stalling doesn't mean that it's doing useful work. Why? You may not be stalling, but you may not, some of the, and this is actually measured at the front end of the processor. So it's really not, it may be on the wrong path, for example, because there may be a branch misprediction. Okay. So that's the paper. We may cover it if we cover prefetching later this year. Later this year. That works, yes. But later this semester also works. And I'm proud of this because this is my PhD. Not because this is my PhD thesis, but because it's good to work on something that you're excited about for your PhD, because that enables you to innovate a whole lot better. If you're given a topic and if you hate that topic, you'll probably not do well in that thing unless you kind of break the box. I prefer having more freedom in selecting topics and giving that freedom in selecting topics. And I was given that freedom in my PhD, and this is something that we have come up with. We're going to talk about that later. And these are some of the papers that we have written, and we have some talks about it. If you're not patient, you can watch the talk if you're interested. And this work won the Test of Time Award 4 years ago at the HPCA conference. And NVIDIA Denver is one of the processors that actually implemented it. They have actually interesting implementation. Okay, so that was my work. That was about 10 years after Dick Seitz's paper, right? Now, fast forward another 10 years. There's another very nice work by Google. It's actually at ISCA in 2015. They published this paper, which analyzed all of their data center workloads according to them. You can see some familiar things like Gmail, search, video, indexing at the time on cutting-edge processors that they use in their data centers. It's a cutting-edge Intel processor. And they have a very nice microarchitectural analysis. The paper, you can see that profiling a warehouse-scale computer. And they wanted to understand the bottlenecks. This is always a good thing to do, actually. When you're trying to optimize something, it's always good to understand what are your bottlenecks in your workloads. And you can see that Dick Seitz did it after they designed their processor. Probably they did before also, but they did after as well. We did it when we were looking at what to investigate together with Intel. Google, I'm sure, does it periodically or maybe every day to understand what are their bottlenecks. But sometimes they publish, once in a blue moon, let's say, which is very sad because if they publish more, hopefully it'll be better for everyone. But anyway, they analyzed where the time is spent on these workloads, and they find out that most of the time, the processor is waiting for data in the backend. There's more microarchitectural analysis in the paper that shows that what fraction of it is cache misses. Actually, I'm going to show that in a little bit. But most of the time, the processor is waiting for data. This is the more detailed microarchitectural analysis, essentially stalled on caches. That's a lot, more than 50% again. Very similar to what we have shown. Now, it's interesting. This retiring part here is actually finishing instructions. So only 10 to 20% of the time, the processor is finishing instructions on these workloads that they execute in their data center. It's good to, again, take a very critical view, right? These systems, what is the goal of a processor? It's to execute a program, meaning finish instructions. It's finishing instructions, meaning doing what it's supposed to do, only 10 to 20% of the time. Does that sound like a good system? You don't need to be 10-year-olds probably to answer that. But if you ask this question to a 10-year-old, they would probably slam you saying that this is a terrible system, go and design something else. They'll be honest. I think we need to be more honest when we design these things. In the current paradigm, it looks okay, but what are we missing, right? Why aren't we finishing instructions 100% of the time? Or at least 20% of the time? 20% is a low bar. Okay, it's good to think about this basically. And this is a very nice paper. I don't know if it's in homework 1 yet because we didn't release homework 1, but maybe we can put it on homework 1 if we didn't. Okay, so essentially, memory is a big bottleneck. And memory, this is actually a slide from 2006. Memory has a lot of components. We're going to look at some systems. You can see in 2006, cores were actually relatively big. And memory started occupying a lot more as people started putting more and more caches. And logic started scaling much better than memory. So there are multiple reasons why memory started dominating the hardware cost of things also. So this is even older. This is 1995. There was a time when you had processors and caches separate. These are separate chips. This is just to give you an idea of how technology scaling has improved, right? People have been reducing the size of the transistors, Moore's law, enabled us to cram more transistors on a single chip. So Moore's law has enabled us to, okay, I'm looking at the wrong thing. Okay, yeah, this way. Moore's law has enabled us to put caches on chip, but that was not always the case, right? And in Pentium 4 in 2000, cache, L2 cache came on chip. You can see that it's occupying a lot of the area. This is fast forward some number of years. This is the Apple M1 SoC. It's not the latest one. But you can see that a lot of the area is really dedicated to caches, right? Even though not all of it is shown. This 8-core GPU, for example, it's not clear what fraction is cache, what fraction is register file. So there's a lot of memory inside even that 8-core GPU thing, or the neural engine, right? Okay, it's easier to see on this picture. This is AMD's flagship processor, circa 2020. You can see that there's a lot of caches over here, right? L3 cache, L2 cache. L1 cache is not included in this green part. So that green part is essentially on-chip memory, SRAM caches. So you can see that a lot of the processor chip is memory. And the cores are here. And cores still have L1 cache, D cache, I cache, etc. Register file somewhere that we cannot see perfectly. And then a lot of the other parts of memory, a lot of the other parts of the chip is dedicated to signaling and interconnect, you can see. So most of the chip is really memory and data movement. This is IBM, which is also a flagship chip in around 2020. You can see that there's a lot of cache here. I don't know where to draw the boundary exactly, but it's a lot. And then there's other stuff like interconnect and memory signaling. So you can see that there's a lot of signaling that happens on the periphery to communicate with the outside, including memory. Okay. This is a GPU at some point in time, and there's a lot of cache over there too. And we want to put more caches, meaning more memory. This is a technology where people can do 3D stacking. You have a processor chip, and on top of this, you can stack something else with some bonding mechanism, with some integration mechanism. And you can see some of the mechanisms over here. I'll not go into that detail right now, at least. But basically, it's beautiful technology to put two dies together on top of each other such that they can communicate. But what it's used for, at least in this particular processor, is to add more caches. So basically, people are trying to patch this memory problem by trying to add more and more caches. And the benefit of this is limited in the end, as people have shown over many, many years. Caches have been growing, but the fraction of time that's spent in memory has not been reducing. In fact, it's been increasing in some cases, as we will see later on. So the question to ask is also, as a critical thinker again, does it really make sense to do this, right? Or are we doing this because this is the thing we can do easily? I would argue that this is the thing we can do more easily than doing something else, or maybe some other things are not as much investigated or thought about. Okay, so basically we have deeper and larger memory hierarchies. This is one system that may be in your pocket. This is a lot of SRAM. There is a bigger part of the system that's a lot of DRAM. And this thing actually has a relatively small amount of DRAM. If you look at a server processor that goes into an, let's say, data center that's executing heavy workloads, that DRAM is much bigger actually. And then there's storage, which is darkness, which is actually not real here, but I just put it over there because there should be storage somewhere, right? It is there. It's kind of darkness because nobody thinks about it. We're so compute-centric in our thinking. That's my point over here. We care a lot about a new chip that comes out, right? People make a big deal. Okay, a new chip came out. What is that chip? It's not a memory chip in general. It's a compute chip, right? Why does it get so much attention? Because we're so processor-centric. This thing can process the data, whereas all of these other things cannot do anything. Well, that's because we designed the system so that they cannot do anything. And as a result, we're having all of these issues with performance, energy, etc. It's good to think about this basically. Okay, and this is it's true for machine learning accelerators also. People are designing a lot of machine learning accelerators, and this is one of them. And in the end, they're bottlenecked by memory, basically. Modern GPUs are also bottlenecked by memory. You can see that people are putting huge amounts of memory on machine learning accelerators like this. Right? Okay. So basically, memory system is most of the platform today. And we've already kind of deconstructed that, right? If you're a 10-year-old, probably it wouldn't be the most of the platform. Maybe we should have 10-year-olds designing systems. Okay, that's a joke, of course, but I think there's some truth to it. Again, it's good to take the approach of a 10-year-old and think a bit more freely. Okay, so that was the need for memory system capacity, bandwidth, quality of service, taken a bit longer. Let's take a look at energy and power. We didn't even talk about that so far. Right? So essentially, things here are much worse, in my opinion. Meaning, there have been a lot of works that show that a large fraction of the system energy is spent on the memory hierarchy. This is work by IBM as early as 2003. And these are studies that they have done on their big iron servers using some commercial workloads. IBM actually designed these systems for a lot of banks use it for legacy reasons also. And they basically showed that more than 40%, up to 50% of the energy in these systems is spent on the off-chip memory hierarchy. Essentially, most of it is DRAM. Off-chip memory hierarchy is DRAM. They have some caches also, actually, off-chip caches at the time. They still have a lot of off-chip caches at IBM. Some of their caches are huge. Like, I think, do you remember the presentation at HPCA? I think they had like 1 terabyte caching overall in their multi-chip modules. So it's almost like memory for many systems, right? So basically, they spend a lot of energy on off-chip memory hierarchy. Some other IBM works actually showed that more than 40% of the power in DRAM. That's also true for GPUs. That's true for some of the works that we have done also. So basically, we have a huge power and energy problem. And there are many issues over here because we're moving data a lot, we're accessing memory a lot, caches are not effective, etc. But there are also other issues like memory consuming power even when it's not used. You need to periodically refresh DRAM because it's a dynamic random access memory and it loses charge over time. And we're going to talk about that problem because that's going to affect a lot of things actually in memory scaling in the next bullet. But let's take a look at this issue a little bit more. Have you seen this slide before? Okay, good. So this is a slide from Bill Daly, who was the chief scientist at NVIDIA. And these numbers are old, as you can see, because the data is 2015. But what remains is the disparity in the energy of computation versus memory access. So essentially, if you look at a 64-bit double precision floating point operation, it's 20 picojoules at the time. A DRAM read or write is 16 nanojoules. That's 800x difference. So over time, things have improved. You can improve people have improved the interconnect technology, signaling technology, made it like low energy signaling, etc. By doing that, you can actually reduce things a little bit. But the disparity between these two operations is very hard to reduce below 150x. Okay, so basically, memory access consumes more than 2 orders of magnitude the energy of a complex addition today. And there are also other costs of energy over here that I'm not going to get into. They're actually interesting. I'm going to give you another reference if you want to look at it in a more methodical way. Then the question becomes, does it really make sense to access memory to get the data to the place where we can do computation, which is the compute chip, or should we do something different, right? Because the amount of energy you spend to get the data to do a very energy simple computation operation is huge, relatively. Right? Of course, it's an optimization problem in the end. The question is, actually, it could be rephrased nicely as an exam question at some point. Maybe we should think about that. What is the amount of reuse that you need to amortize the energy cost of this data movement, given these numbers? And people have done those studies, and they find out that you need to reuse the data element hundreds or thousands of times so that you can overcome the energy cost, because you need to you're operating on many data elements at a time, right? So basically, the idea is, then the question, of course, becomes, is that level of reuse prevalent in workloads today? And in most workloads, the answer is no, essentially. Even though people have tried to actually optimize for reuse automatically or by changing the programs, it's very hard to get that levels of reuse in general across a wide variety of programs. Some individual programs you can get that reuse, but a wide variety of programs, it's very hard to get those levels of reuse. As a result, energy is wasted on moving data from main memory to the processor chip. That's good to think about this again, right? Again, take that critical view. And again, if you take this to a 10-year-old kid and explain it nicely, maybe they will tell you, maybe they will come up with the idea of just do that green thing over here in that black place, right? With their explanation, right? I was a 10-year-old kid explaining processing in memory for you right now. I think it's good to think about that, right? Okay, anyway, so that was a complicated arithmetic operation. What about a simple one? Well, simpler one. It's not simple. 32-bit addition, integer. This is actually data from an accelerator paper that Bill Daly's group wrote in ISCA 2016. So you can find all of these numbers over there. But essentially, a simple or simpler arithmetic operation is much more, increase the disparity much more. And that disparity becomes 6400x, assuming all of those numbers from that paper, which are reasonable numbers. But again, maybe the real number is 1500x, 2000x maybe, not 6400x. Still, that's fine, right? Because over time, interconnects also improve, but at some point you run into diminishing returns on how well you can optimize the energy efficiency of an interconnect. Okay, so 6400x, that's a lot of energy differential to overcome if you want to amortize the energy cost, right? So basically, we're wasting a lot of energy moving data from main memory to the processor chip. And we're not even talking about storage yet, because the data, if you think about the data flow, it comes from sensors, goes into storage, and from storage goes to memory, from memory goes into caches, caches goes into other caches, and eventually goes into the registers, and then you process them over there, or some buffer. So if you talk about storage, multiply this number by another 10x or so, depending on the storage. So that number goes crazy, essentially. Of course, we're not paying that cost every time, cost differential every time, because there is some locality in the programs, and we should optimize more for locality. But we're paying that cost enough times that this is actually dominating the energy consumption that we have in our systems. And today, we also don't want complicated arithmetic. Well, I actually take that back. I think when it makes sense, we want complicated arithmetic. But because energy is gone so crazy and people have figured out how to get similar accuracies with smaller precision and lower complexity data types in machine learning especially, which is a very old idea actually, but they applied it to machine learning, and there are lots of hundreds of papers on machine learning, on quantization, which has become very boring, on how to actually use smaller data types, etc. And people have shown that you can reduce the computation complexity, meaning you can do, for example, or you want to do 8-bit integer addition as opposed to 32 bits or multiplication. Or you want to do even 4 bits, right? Or 2 bits. Ideally, you want to operate on single bits. You want to represent your weights and data with single bits and operate on using binary neural networks. The problem is people have not figured out how to do accurate, let's say, ML tasks using binary neural networks. But the push is there so that the reason is to reduce the energy. Now, if you reduce the complexity of computation, that reduces the energy of computation, clearly. If you, for example, do 1-bit integer addition as opposed to 32 bits, intuitively, you should be able to reduce the energy of this by 32 times, right? Intuitively, give or take some things, because it's not exactly linear, but you should be able to play some tricks to get it almost linear, yes. Well, certainly heat dissipation is part of it, right? If you consume a lot of energy, you need to have power limits that are higher. And you need to design your processor such that it's tolerant and robust under those conditions. It affects your cost in the end. But also there's and it affects your power cost also, right? You need to actually provide power supply. So all of them basically. And also the battery life, right? If you're actually using these things in a battery constrained environment, your energy will drain your battery quickly. So it actually affects all of those. And also there's another part that is hidden, which is if you're consuming so much energy on this or something, you're wasting performance, meaning you cannot do something else, right? Yeah. So there's an opportunity cost as well. So, okay, if you reduce the, let's say, bit width of arithmetic operations, you reduce the energy of computation. You also reduce the energy of data, depends on how you pack the data, etc. But the amount of energy you reduce from the computation is much more than the amount of energy that you reduce from the data moment. So this becomes a bigger bottleneck as you reduce the data type complexity. Yes. Mm-hmm. Yeah. Yeah. Depends on how your data is laid out, right? You need to lay out your data nicely. Yeah. Say it again. I couldn't hear. Yeah. That's true. Yes, I'm not sure about more. Why would you reduce data moment more? Like you need to. You certainly reduce computation energy, right? By reducing your adder, let's say. But to reduce your data moment, you need to ensure the data is laid out nicely, right? For example, if your data is laid out in an odd way, and it's not at the boundary of caches, for example, you don't pack your data nicely in a cache. Then you're not going to reduce your data moment, right? You're going to move some data that may not be needed. So you need to play tricks to reduce the data moment additionally. I agree, you can reduce it, but you need to play more tricks. Whereas reducing the complexity of the computation directly reduces its energy, right? Because you're already getting rid of a complicated adder, let's say. Okay? Okay, good. Okay, let's move on. So we did a lot of studies to really understand and quantify the effect of data moment and memory, in general, memory on energy, as well as performance. I'm going to give you, since we're talking about energy right now, I'm going to give you some energy results. And this is a study that we did with Google some number of years ago, where we analyzed some of the workloads that are used in mobile systems, like TensorFlow inference, Chrome browser, video encoding and decoding. And we found out that on average use cases, based on at least the user studies that we had access to at Google, more than 60% of the total system energy spent on data moments in this mobile system, moving data across the memory hierarchy, on average use case. And the worst cases, it could actually be much more. We're going to talk about this more when we talk about processing near memory, because one of the main proposals that we have is to do processing near memory so that we avoid that data moment as much as possible. We repeated the study again with Google on more machine learning workloads, neural network models that are used at Google using edge TPU devices. I've shown you a picture of this earlier today. And we found out that more than 90% of the total system energy spent on memory in large machine learning models at the time being used at Google. This is an example from that paper, that study essentially. And you can see different machine learning models, convolutional neural networks, recurrent neural networks, etc. But the LSTMs and transducers were the largest networks and edge devices at the time that we studied. And you can see that this is the normalized energy consumption. Essentially, most of the energy consumption is spent on the off-chip interconnect and DRAM, because the buffers are not very useful in this case. Okay, that's true for a lot of the other workloads also. There's other interconnects, etc. But we can actually improve both performance and energy by doing computation somewhere else. And that was our proposal also in that work. But we're going to get to that as well. But this is to give you an idea of these numbers. Essentially, I think a lot of these numbers point out that we do not want to move data. And you can achieve this by optimizing the current systems as much as possible, keeping the current paradigm, like what you discussed, right? If you do quantization as much as possible and do your data mapping nicely, you can reduce the data moment as much as possible. But that doesn't fundamentally get rid of a lot of the data moment in the end. So we want to actually, or that doesn't fundamentally enable something different. right? You're basically optimizing an existing system as much as possible. And then there will be another application that will come that will require these higher bit widths, etc. And then you're back to square one, right? And you'll have to figure out everything. So maybe there's a better way of designing systems, essentially, right? And that's what we're going to talk a lot about in the next few lectures. And we're going to talk about memory-centric computing. Essentially, we need a paradigm shift that enables computation with minimal data moments, which is essentially enabling computation capability in other places than the processor, where data resides or where data is generated. And this requires us to think a little bit more data-centric. We would like to make computing architectures much more data-centric. So there are many places where we can process data. And today we're restricting ourselves to compute units inside this SRAM-dominated chips. Or there are many places inside this chip also where we can process the data, but we're not doing it yet. And then there's DRAM, and then there's storage, and then there's sensors. Why don't we have actually computation capability and processors in all of those places? And then the task becomes how to actually distribute the tasks, computation tasks, across all of these different, let's say, processors. Let's call them processors. That enables more things than what we can do today, essentially. But we're going to examine this idea a lot in the first few lectures. Let me give you a little bit more in this direction. Again, we're talking conceptually over here. We're going to focus a lot on memory, main memory, and storage in these lectures. And if you think about main memory and storage today, we actually store almost entire applications in there. If ideally we would like to fit everything in main memory, DRAM, right? Ideally we would like to fit everything in caches, right? So with the processor-centric model at least, then we don't need to go to memory. But that doesn't work. So ideally we would like to fit everything in memory so that we don't need to go to storage. When that doesn't work, we want to fit everything in storage so that we don't need to go to a larger storage somewhere else, right? So we try to fit a lot of applications in main memory, and main memory has huge sizes today. So in processing inside memory or storage, we would like to be able to query the memory and storage device, ask it questions like, can I execute something on you? And if the storage device says yes, or if you know that the storage device can execute that, it hopefully does that execution and returns the results. So there are many questions over here, which we're going to cover over the course of some number of lectures. How do you design the compute-capable memory and storage devices such that you can do, hopefully, some interesting computation? And also, we'll ask the question, what are the fundamental capabilities of some of these memory and storage devices that enable it to do computation naturally, let's say, because of its analog operational properties? So this is going to be interesting, I think. And then how do we design the processors and communication units to make sure this works, something like this works? And I think an important direction is, once you have computation capability elsewhere, what kind of processor would you design here as well as there, right? It's also good to think about it, because the processor that we design today is designed assuming that computation is not done anywhere else, essentially. Once that assumption changes, you may need to rethink the system entirely. So it's good to think about that. And how do you design the software and hardware interfaces to enable this sort of processing somewhere else? How do you design the system software, compilers, and language? And there's a lot of opportunity in all of these directions, I would say, to actually make it easy for people to use it. Because if you give it to someone who's doing Python, they're not going to tell what should be executed where, right? They need some help. Or ideally, they don't want to do anything, right? Actually, not ideally. They don't want to do anything. So basically, you need to design the system stack to make it work for existing applications with minimal changes, or ideally no changes at all. And then how do you design the algorithms to take advantage of the underlying substrate and maybe put it into libraries so that people can use more easily? Because the underlying substrates may have some computation capability, but existing algorithms may not be optimized for that, right? In fact, existing algorithms are not optimized for doing execution on the memory side at all, because there's no such thing that people have considered. It's optimized for a processor-centric paradigm, maybe over time accelerator paradigms, right? And one of my favorites is here, theoretical foundations, which is really related to algorithms in the end. But we also need to develop a more memory-centric theory of computing. So if you want to quantify the complexity of algorithms today, what do you do? Does anybody know? How do you decide whether one algorithm is better than another from a theoretical perspective? Anybody? Exactly. Small or big O notation, basically. Big O, big theta, big O, small o, whatever. And what do you do? How do you compute big O? Okay, do it by hand. But what does big O stand for? What is the order of magnitude? What are you looking at? Huh? It's basically how many operations you do, right? That's true, right? Yeah. It's a representation of the order of magnitude of operations that the algorithm performs. But maybe that's not as important, or maybe that's not as precise, right? As we've discussed, right? The question is, does it take into account data moment? It doesn't, I think, at least not directly. It's much more, let's say, processor-centric. Processor is doing these operations, so I should minimize those operations from an order of magnitude perspective, right? That gives us a better algorithm, hopefully. Maybe not. Is it better in terms of performance? Not sure. Is it better in terms of energy? Can it distinguish the data moment? So it's good to think about these questions, basically. I think computing theory is very processor-centric today. It's not designed with the mindset that computation is performed in the memory, for example. Or it's not designed to take into account the data moment operations, at least explicitly. So there's a lot more potential for improvement over there. So we don't have a data-centric theory of computation, essentially. So this is actually something that spans across the stack, this whole processing in memory storage. It's all the way from devices to algorithms, including theory. So we're going to spend some time on this, which is going to be very interesting. And I think it's very interesting to look at this today, because there are actually real devices, real UpMem devices, for example, that where you can get your hands on, and you're going to do that in this course. And you can actually develop programming models for them, which we have done. We may actually have a lecture on that later on. You can develop compilers for processing in memory architectures. You can also develop hardware, of course, and algorithms, of course, for all of those. So we'll cover a lot of works in this direction. So there's a lot to do over here. And this is the paper that I mentioned that is kind of like a book right now that covers things in a way similar to how we're going to cover it. But it's also 99 pages, so I don't ask you to read it. But we're going to cover a distilled version of it in these lectures. Okay. Any questions? Okay. So let me cover the rest of it. We're not going to be able to finish it. I'm going relatively slowly, but it's good that people are asking questions. No questions? Otherwise, I'm going to jump into a technology scaling issue. Yes? This one. Okay, I see. Well, we'll see different ways of designing things on the memory side, but it's not going to be the same as adding. Basically, it's not going to be replicating the same processor on the memory side for various reasons. First of all, you will not need that much cache on that side, so it's going to be a huge waste if you actually put something over there. It's kind of a waste of area also. So it's going to be, we're going to design the processors with the constraints in mind over there. And your data moment is very little over there, or at least relatively little, that you will need some caching on the other side, but those caches will be much smaller. Yes? Okay, we're going to see all of those also, yes, but what do you mean exactly? DRAM is acting as a cache for this processor? That's true. Currently, the DRAM acts as like a buffer or cache. A combination of, I would say DRAM is really a buffer / cache that serves the processor today. That's true. But I think his question was basically, if you're adding a processor over here to process things, is it the same thing as kind of replicating this processor with large caches over here? So it's not going to be the same thing for various reasons. But we're also going to see methods where you can use DRAM, part of DRAM as a cache, which is going to be interesting for the processors over there. So you're kind of prefetching or thinking about a lot of interesting things that people have done. Okay, so let me quickly cover this part. We're not going to finish it, but this is also a fascinating part. Essentially, we have a problem. even though we demand more from memory in all of the metrics, we're not going to get more easily, at least, unless we get rid of robustness issue. Unless basically we're not going to get more easily because technology scaling is becoming more difficult. Ending, I've been saying that for a long time, but ending is always a nebulous term. Basically, the size of a DRAM cell, dynamic random access memory cell, has been reducing, but it's not. It's become harder to reduce the size of that cell. Meaning, capacity is hard to improve, energy is hard to improve, latency is hard to improve because scaling has provided a lot of these benefits over here. And difficulties in scaling create robustness problems, as we will see. So this is a fascinating area that we will cover. I'm going to give you a few examples relatively quickly. So we've done a lot of work in this area. This is a paper that I used to recommend. It's an old paper, as you can see, or relatively old paper, where we argued that these scaling issues will become worse. And more recently, we were invited to write a paper to the same conference 12 years later. And we basically said that the issues are much worse today. So we need to do more. But good things have happened in the last some number of years. I'm going to give you why this is happening. Essentially, if you look at DRAM, dynamic random access memory, this is a virtual picture. You have a capacitor. That capacitor stores some charge. Whether or not you have a charged capacitor represents whether or not you have a 0 or 1, essentially. And there's an access transistor. This is a single bit, basically. There's an access transistor that you enable. And when you enable that, this charge gets shared with a bit line that's set to a reference voltage. And whether this charge perturbs the bit line in a positive direction or negative direction determines how you sense the charge. Basically, if it perturbs in a positive direction, the sense amplifier will amplify the voltage to the highest level, and you will read a 1. Otherwise, it'll perturb things to the lower level, and sense amplifier will amplify the voltage to 0, and you'll read a 0, essentially. That's the idea. This is the fundamentals of how DRAM works. If you haven't seen it before, now you've seen it. It's kind of an assumed knowledge, but it's good to go over the fundamentals. And this is a single cell over here. What you have in DRAM is you have many of these cells, billions of these cells in a single chip. We're going to see how it's structured a little bit more later on. But essentially, this is charge-based memory. You have charge stored in capacitor, and you try to sense the charge, right? How much charge there is. So clearly, there's some noise threshold over here. If your charge is very close to the noise threshold, you can actually get a wrong sensing. So you should really store charge nicely over here, meaning either at close to VDD, highest voltage, or 0, lowest voltage. But for this to work correctly, capacitor should be large enough for reliable sensing. And the access transistor should also be large enough for low leakage and high retention, because normally this path, it looks nice like this, but transistor is never a perfect switch. If you actually close the word line, meaning, if you close the word line, normally you should really disconnect this path, but it's never disconnected. There's always some leakage. So a capacitor leaks over this path. And as a result, what you get is over time, you lose charge. That's the dynamic nature of DRAM memory. And as you reduce the size of the capacitor and the size of the access transistor, you have less charge and you have more leakage, essentially. And also, you're more vulnerable to noise. So basically, what we've been doing is we've been reducing the size of this so that we could get a more than 1,000,000x improvement in the last 54 years, 50 plus years, as you have seen earlier. The question is, has this come at a cost? And it has come at a cost. I'm going to show you a bunch of results. Well, maybe today, maybe later. But basically, it's become hard to reduce the size of this capacitor without running into reliability problems. So noise has become too much, let's say. Okay, let me give you a more realistic picture. That's a terrible picture. I should really fix this. But basically, this is what DRAM cells kind of look like. This is the capacitor today. Okay, maybe I have a better picture. Let's go. Okay, so this is what the capacitor kind of looks like. It's really etched into the substrate using a three-dimensional, right? It's really a three-dimensional thing. This is the bit line, that's the word line, etc. And this is the transistor. So you can see that really it looks a little bit different. And people actually go through a lot of hoops to make that capacitor store as much charge as possible. But as you reduce the sizes of everything, the amount of charge that you're going to get in this capacitor is going to be lower and lower. And things are very close to each other, as you can see. We're going to get more into it. So this is basically the scaling problem. It's very difficult to reduce the size to begin with. And once you reduce the size with a lot of techniques and fabrication, etc., you run into robustness issues. And this is true for flash memory as well. We're going to cover flash memory. These are charge-based memories. That was DRAM and this was flash. I will not go into it right now, but essentially it's also a charge-based memory. You store charge and you detect the charge level. And essentially it becomes, as you reduce the size of these cells, it becomes difficult to place charge as well as control charge. And you run into a lot of noise issues, meaning data retention and reliable sensing becomes difficult as charge storage unit size reduces. So we're going to look at a lot of issues related to this, but we have been studying this problem for a long time. This is one study that we did. So how do you study this sort of problem, right? One thing you can do is test real DRAM chips. We're going to do that. Another thing you can do is figure out what kind of errors you're getting in the field. And it's always good to do different types of studies. Another thing you can do is try to do simulation. We're going to talk about simulation later in this course. There are some possibilities, but also have some downsides. So if you can get your hand on data on what's happening in real chips, it's always good for you to really find new ideas, new directions, even make new discoveries, as I'm going to show you over many years. So this is a work that we did with Facebook. We studied the memory errors that happen in their data centers. This is all of their data centers across the world. And it's a lot of memory, actually. They have a lot of memory, at the time. We're talking about 2013, 14. That's when we collect the data. We published the paper in 2015. Today, it's much higher, of course. But essentially, we wanted to understand what kind of errors are happening in chips. And this is one of the major findings that we have. This is the chip density employed in the production data center, DRAM, essentially, DRAM chip density, where today we're at 16 gigabits on these chips. Maybe 32 gigabits are coming, actually. And this is the relative failure rate of the servers. It's some normalized metric because these are different servers with different things, right? But in the end, the takeaway is that servers that have denser chips experience failures more. This is because they see more memory errors, essentially. And these are failures that affect applications, that affect systems. Some of them require someone going and changing the memory, etc., to work. Basically, that's the key takeaway. There's a strong correlation between the size or density of the memory chip, DRAM chip, and the error rate that you get on the servers. That sounds interesting, right? So there's clear correlation is not causation, but in this case, there is a very strong causal reasoning because these errors, and we have found in many cases that these errors actually lead to failure of the servers. Okay, this is a paper. It's actually interesting work, I think, and I would recommend people to do this sort of studies if they can. Not so easy as companies become more, let's say, secretive. And sometimes they do become more secretive. Okay, we also built a lot of experimental infrastructure to really test DRAM chips. I'm going to introduce those infrastructures, but then we're going to stop. This is in 2011, we built this infrastructure to test. It's an FPGA-based infrastructure where we have a memory controller that we can program, and we can attach DRAM chips, different DRAM chips to it, and then we can test DRAM chips. And these are some papers that we have written. This is the RowHammer paper. I'm going to talk about that soon. This is where we did a lot of the RowHammer testing experiments. Again, a lot of FPGAs attached to a server, essentially. We released this open source, DRAM Bender. Well, this is the SoftMC version of it. And people have been using it both in industry and academia, which is fascinating. This is the more recent version, DRAM Bender, which is more capable because it can test HBM chips as well as DDR4 chips. And you can see we can do different studies by changing the timing parameters, temperature, voltage, access patterns. You can essentially put DRAM chip under any condition you want, as much as you're physically capable, of course, and also change the timing parameters with which you access, change the order of accesses, because you have a soft memory controller, and hence the name SoftMC, that you can program using an FPGA, essentially. FPGA has a soft memory controller. So we did a lot of experiments with this. This is our laboratory in the F floor of ETZ building that many people are familiar with over here. Some usual suspects are not here, but some suspects are here. And we still need to unpack those FPGAs, 25 FPGAs that should increase our capacity a little bit more. Okay, I think I should not go further, but what do you do with this infrastructure is something you may want to ask yourself. Why are people building? By people meaning us. And this is one of a kind infrastructure in the entire world. Other people have used our open source versions and they built their infrastructures, but I don't think there's anything at this scale, including in DRAM companies who are supposed to be doing this for their bread and butter. But again, the good question to ask is, what can you do with this infrastructure? What can you discover? How do you analyze memory chips? And we're going to talk about that starting next week, next Wednesday. So this is probably a good teaser to keep your mind busy, because those are good questions to ask actually to discover new things in existing chips. Okay, any burning questions? Okay, otherwise we're done. Have a good weekend. I'll see you next week, next Thursday.